Y esto lo cierro para que luego no se... Lo voy a tener aquí abierto por si. ¿El qué? ¿Tres qué? Ah, 3 es la de Drogovolsky, que no viene. Y la 2 es la de Filipo, que no la subió. Como va a hacer esto también.
Ah, claro. ¿Por qué pensaba yo que era la siguiente sesión? Mejor así.
Sí, es la siguiente que...
No pendiente.
Ah,
Pensaba que era así. Vale, perfecto. O sea que realmente hay que poner solo esta y la dejamos.
sí. Sí, pero voy a tener esta abierta por si...
Sí. Hacer esto.
Vale. Ya está.
Lo primero que sí, y luego ya lo también.
Ya hemos llegado.
¿Sabes que ahí son muy populares?
Lo dije, eso va.
Estrella, esto y eligen igual. Que te tenéis que funcionar, si no van a gustar,
Son todos muchísimo.
y la de. A ver, no sé cómo para el momento me lo guarda, cuenta de vida no puede ir, sinceramente.
Sí, sí. Total, hubo una maestra que te va a decir.
Sí, claro, sí, hubo una. Yo voy a ir con Isabel, como tenemos. Bueno, a ver si no lo digo. Va.
Con la mano de interés.
No, porque además sabes qué pasa, ayer no tuvimos posible esto que estamos en
A ver.
No. Te había dejado, me pasó por el estudio de abajo, la mochila no llevo cosas que no se me había dejado. Le he visto todo. He dado cuenta aquí, pero no entiendo que dejar otra cosa. Rápidamente, vamos. Esto le lleva al coche. Si no tenemos un sitio donde yo dejaba las despachos, me descalada.
Sí, es un poco ruido.
Porque tengo la mochila, ¿no? Voy al metro y digo, si la roban, yo qué sé.
Bueno, ¿y bien esta mañana?
Y yo digo, sí. Es lo que sí se suele acordar, aunque parezca que no, pero se suele acordar.
Si no te pones tú.
Vale, luego no sé qué me pienso que tengo que controlar.
A ver, ahí.
Sí, yo voy a cambiar. Un modelo, si quieres llamar que tiene cuánto tiempo tiene cada uno, ahí hay algo que funcionar con algo, o sea, después estás ahí en la ¿no? Bueno. Seguro. Como el primero,
Sí, claro.
No, para mí, pero
Sí, sí.
Really like this.
Yeah. Just checking because the question is problem is that with mouse, this pointer. So in order to
Yeah, there is no point.
yeah, well, there is pointer, but then those from Zoom cannot see it, so then one has to use mouse to point.
I mean, how many are?
I will try with mouse to see.
There's a button. Hi. Can you use the mouse? I don't have the mouse on.
What? You don't have it?
No, when I go on viewer.
Well, actually, it's not clear whether with Zoom it will. Should check. I just shuffle the slides. I just check.
Can you stress this of right so vision?
Yeah, well, try to.
I mean,
Sure.
a few
Yeah,
words,
yeah.
such as the next day.
Well, try to make the refreshment.
So you talk about spinning channels.
Okay, yeah, you want to take the range.
Yeah.
If you want, you can try this one. Because I think we'll be
Yeah,
starting
well,
soon.
actually, should start.
Oh,
No.
no, wait a little bit for the. Yeah?
Let's just come
Ah,
again.
Maybe here.
Now share screen.
From there, yeah.
Okay, now the question: do
Yeah, it can be seen.
so?
If you want, you can click here to make this smaller, to minimize this,
Yeah.
so it doesn't bother you. Yeah.
But now
Yeah.
like this.
Okay.
Okay.
So we'll wait for the chairman to review it.
Just a second. Let's check.
So before we start the session, let me make an announcement. So as you know, Alexander, he is from Ukraine, and actually he is now in Vienna. He's a professor, but he had to take the leave to help in the crisis of the refugees and to help in the medical supply. So he was unable to come, and therefore what we are going to do is we are going to give a few minutes more to the speakers, and then at the end we are going to send an applause to Alexander. Okay.
Because we are to start session 8, what is matter. And the first speaker is Professor Michael EPH Studies. The title is Resistivity and the counter response inside superconductor.
Can you hear me? What's microphone? Okay. So, thanks, Herman, for organizing this meeting. Well, there were few conferences that I was over Corona time, which were hybrid, and in few of them, there were like 2-3 people in the audience, and the rest was on Zoom. And the second day of the conference, I was the only one who was giving presentation in presence, so which was kind of. And here I see it's really going back to normal life, which everyone appreciates. So I will talk about flux creep and the Campbell response the two superconductors. So I will try to make introduction to strong pinning and show our last published paper on that, which was work done by Filippo, who is here and will give next talk. And in his talk, he will tell how everything is different if we consider not isotropic defects, which we did for 20 years, but generic and isotropic defect, then actually it seems that all like geometry and so on is quite different. So since I'm kind of first here about vortices, I should tell a bit what is pinning in general and strong pinning. So we have vortex lattice, so these are vortices, and then some defects, and we want to calculate the pinning force with which defect hold our lattice. So this spinning force gives us critical current, and well, we all know that critical current is of major importance in superconducting magnets and so on. So this problem of calculating mean pinning force can be split into two forces, into two problems. First one is find actually the force of interaction of the lattice with a given defect. And this problem kind of philosophically is simple. If you know what defect is, then it's not a big deal to calculate pinning force. If you say it's like some void in superconductor or like some normal inclusion or twinning boundary and so on, then for all of them one can calculate interaction of this with the vortex lattice. Well, the problem which we have, of course, is that usually we don't know what are the effects that produce pinning. But much more conceptually difficult problem is the second one, is the average this force over randomly positioned effects, because some pinning centers push vortices in one direction, other in another direction, and so on, and they're randomly positioned, and then we have a really complicated problem of strongly interacting vortices in the presence of random potentials. So kind of there's no solution to that. But this problem allows quite a dramatic simplification if we have low concentration of pinning centers. So if defects are rare and far away. Well, it's called strong pinning, which is in some way a bit unfortunate notation, because when defects are rare and far away, then of course pinning force cannot be large because there are just few defects, but historically it's called strong. And in this situation, one can reduce complicated averaging over many defects by averaging of pinning force of single defects, and then just multiply by density of defects. And this allows us to have quantitative results. So what one studies interaction of pinning centers with the vortex lattice, and then as a result, one obtains this kind of self-consistent equation, which looks simple but not completely simple. So the meaning is that displacement of vortex is given by force, and the C bar is effective elasticity, so it's made from elastic constant and so on. But the thing is that this is nonlinear equation because displacement depends not on the force applied to non-interacting vortex, but at the force applied to already displaced vortex, and this we have, that's why here says x plus u. So we have nonlinear equation, which, well, not always is easy to solve. So we are doing kind of this strong pinning for over 20 years, and every time we make this introduction and so on and so forth, but after, from the discussion afterwards, I understand that one has to do it another and another time again. So this interaction, displacement proportional force, can be put together to effective energy. So what we have to consider is behavior of this problem, that we have pinning energy in this potential well, and effective interaction of vortex. So now R is coordinate x plus u, so just distance to defect, and then interaction of vortex with all other defects in this situation is given by parabola. So we have effective elasticity, which kind of is parabola, or some other applications called cage potential. Now we move vortex lattice through defect, and this corresponds to moving this parabola. And now interesting thing appears if effective pinning potential is rather strong, such that maximal maximal second derivative of potential divided by elasticity is bigger than 1. And then this energy has multiple solutions. So what it means multiple solution, that is here. So we go even further, and then we move vortex like this, and now the upper solution appeared. It has higher energy, so vortex doesn't want to jump to defect. Yes, so here it appears. We continue. Now they are on the same energy, so here we have this line crossing. So, but vortex will jump to the pin much later when this solution disappears. We go further and further, and now again we reach this point, but vortex doesn't go there. It's quite metastable state. It has higher energies, so we are almost here. It would like to be in the minimum of parabola, but it cannot go there because there is this little barrier, and eventually it will jump there only with this M. Right. So geometry of the process is the following. This is this black dot. Well, is some pink, or let's say blue circle with its effective potential. This is the shape of vortex line along Z. Now we move it, and when it comes to this point, then it jumps to the pin. This was kind of the first jump. We move, so more position at infinity far away is here. So we move far away, vortex lattice, but the tip is still sitting at effective, it's pinned. And only when we move bigger than some distance x plus, then we jump back out of. And this is this geometry. Now, if we look on transverse, if we look now, this axis will be not x and y. So this what I showed was head-on collision when we go straight through defect, through the center of the second defect. Here assumed to be a sphere or cylinder. Now, if we go at some distance, then again, as soon as we reach, if the pinning force is radial and it's symmetric, doesn't depend on the angle, then as soon as we come to this distance, we jump and everything clicks. But if we move at some distance far away, then we never come close to this x minus, and there is no jump, and here vortex average force is actually 0. So this is geometry for isotropic situation. Now what Philippe will tell that in an isotropic situation everything looks quite different. So we can calculate the pinning force, the average force which pins exert. So we integrate it over displacement and over transverse. So transverse thing that here we don't have pinning force. Now when we integrate over displacement, then we see that force is gradient of potential. So when we integrate derivative, we have to get function at the boundaries. So if function is single valued, then at the boundaries, this function is the same far away, pinning energy is the same, and we'll get 0. So we only get non-zero if there are jumps, and the average pinning force is given by the sum of the jumps. So this is the result. And that gives a critical current. So this goes back to Labush and Larkin-Ovchinnikov, more than 50 years ago. Now, one thing that we tried to think was about calculating current voltage curve. And actually, many people were, like this is from review of Pierre Ledoussal, drawing this type of IV curve. And well, if I was asked before, kind of going to this, I will also draw that, but somehow never managed to publish it, fortunately, because if we try to calculate it, then we get this shifted linear IV. That's what we did with Alex Thoman. So what we have is flux flow, as if there is no pinning, but shifted by the value of critical current. And this actually reminds, or is some sense the same as so-called Coulomb law of dry friction, which states that kinetic friction is independent of sliding velocity. That friction force which needs to start sliding is the same as friction force where, well, Coulomb observed it and measured it, and I don't know whether in tribology there is an understanding of this, but for vortices we can derive this law. One can ask whether it really agrees with experiment, and this is the old, so to say, textbook data by Kim and co-authors. So this is flux flow. Actually, this experiment is famous for the flux flow resistivity, so which we know as Barney-Stephen, but actually these people were first in '64 to observe that actually this slope is proportional to the field, and in '65 Barney and Stephen made their theory for flux flow. So this is not the first observation of flux flow, but Barney and Stephen gave the first explanation of this finding. So that's why it's kind of famous paper. But if you see IV, so then you just see shifted linear IV with some little curvature here, and that's kind of for different samples with different fields, there will be different slope, but also like shifted linear IV. And there are numbers of other more recent experiments which I show this feature. And please, for a moment, just keep in mind this curvature because I will talk about this later. So this is kind of two different possibility, and a strong opinion it is like this. And actually, the result of creep, what I will show is that the shifted linear gets shifted to the left and acquires curvature. So how does one treat creep? So first, what happens without creep? So we have vortex which goes along this, jumps at the end of the branch, goes up, jumps at the end of the branch. Now, if there is thermal fluctuation, then vortex can jump actually earlier from one branch to another, just overcoming the barrier. And this corresponds on this picture that we follow. And now there is another minimum, it's higher, so vortex can go up there. Well, if it goes there, then it will quickly go back. But for example, if we are in this situation, then this already is lower than its initial state. So if it comes here, it will stay here longer. And so we get jump not at the end, but earlier. And the barrier which vortex have to overcome, so here, this coordinate is just the difference between blue line and the dashed line and the small value potential. So one can write kinetic equation, calculate probability to go from one branch to another and backwards, put it all together, and then as a result of it, we get a shift of branch occupation. So here, this dashed line is not really there because vortex will go over the barrier before and the jump will shift here. The position of the jump depends on the vortex velocity. So if vortex moves very fast, then there is not so much time to probe for thermal activation, and the shift is somewhere here close to the endpoint. But if the vortex moves slower, so for low drive or low voltages, then the system has much time to probe thermal fluctuation, and the shift will be here. So knowing velocity, we can calculate position of the jump knowing position of the jump, we can calculate the pinning force, and as a result, we get IV. So in this sense, it's inverse to what usually one does. Usually one assumes force, calculate response. Here we can start with velocity and calculate force and get this equation. And at low temperature, the position of the creep is kind of low, the position of the jump is close to the end point, and expanding here it's similar to usual Landau theory of Taylor expansion. Then we get the barriers grows like change in the power, change in distance, the power of 3/2, and effective barrier goes like JC minus J power of 3/2. At low velocity, jumps goes here to the crossing, and we should do a bit more than tricky thing. We should look how distribution function changes near the thing, and then we get actually this model linear IV. So we have linear IV here, which may be exponentially weaker, unmeasurable, and curvature. And this actually, if you remember early days of ITC, there was studies where people measured linear resistivity, which was thermally activated. So Tinkham actually compared some experiments with some fit to Ambiga Halperin, and in the second edition of his book, but this was never properly understood. Here, at least, we have some knowledge I can give them. So this are numerical plot of this formula, and you see now effective creep is just the same linear with some curvature. There is linear IV here. Well, there are numbers like 10 minus 3, 10 minus 4, 10 minus 15. So this is for different temperature over pinning energies. So we change it, let's say, factor 2. And here, since it's exponential, then it gets very small exponent. So you may not see anything here. And now I just should remind you that this data of Kim looks like straight line with a little bit curvature. So, well, we couldn't ask them to send us the data, but we had some other people with whom we could get the data. And here we analyze this. One was relatively old data by group of Eva Andre. They actually observed shifted linear, and then we asked if they have also some data finite temperature. And another recent work by Tata Institute group by Pratap. And dotted lines, dotted are experimental points, and line is fit to this formula. So fit to the theory, and actually when Martin did it, I was really shocked that I never thought that one fit experiment with such accuracy, because, you know, these are not parabola or straight line, that's rather complicated curve, which I think have the data really perfectly. It's rather not so simple thing how to make the fit. So this original data set, okay, probably we're running out of time, so let's kind of quickly skip it. Because we don't come to Campbell. Yeah, sorry. Well, I don't want to. I have still half of my talks, so I don't want to exaggerate. No, I'm not finishing, but I don't want to exaggerate. So, it's conclusion of this part. So yeah, it was just. Now we come to Campbell length, and well, Campbell length due to Archie Campbell, who passed away 2 years ago, and. It's nice obituary written by his wife in The Guardian. And well, it's written there, he is known as the Campbell technique. Yes, so that's also Archie and some of World's conferences. So what is Campbell length? So Campbell length is actually the same type of, is a penetration length for small AC field, but in the presence of large DC field. So it's measured in the same way as longer penetration depth with the same kind of technique. The only difference is that there are already vortices. So it responds to a small, it's linear response to external AC field, but contrary to London, it is when we already have large DC field. And then what happens here is when we apply AC fields, so vortices are pushed by the Meissner current, but since they are pinned, this displacement doesn't propagate inside and is screened by some length. So that's kind of picture type thing. So other pictures which one can think is if we are in a rush hour in the public transport, so don't do it at Corona time, then as you see, it's very difficult to push people inside the bus or the tram, but those who are inside, they don't really feel it. And if you were like really have traffic in the public transport, then you can really experience it when you try to get it and you fight your life because with this bus, if you don't catch it, you will not get your plane or something. But if you stay inside, then you even don't notice that there's some perturbation coming there. Well, just because you are pinned and this perturbation is not propagated. So how to describe it? So there, what Archie Campbell suggested. So we have force balance equation. So this is Barney-Stephen viscosity, which is irrelevant for us. This is the compression of vortex lattice and that spinning force. And we have external drive. Now we replace, so Campbell replaced spinning force by parabola here. So then the spinning force was linear in displacement, and curvature of parabola is called Campbell curvature. And then this Campbell curvature, inverse Campbell curvature, gives square of the penetration length. Now, if we want really to do average, then we should take into account that not every, so in the Campbell formalism, he assumed that every vortex is at the bottom of potential well, and then there is kind of the same curvature everywhere. Now, for random disorder, some vortices can be at the bottom, some can be at the top, some curvature is positive, some it's negative. What we have to do, we have to average it. And when we do this averaging, so this work done with Roland, also here, then it's in simplified manner, pinning force, critical current is average of pinning force, and the force is gradient of energy, so we have jump in energy. But Campbell length is given by average curvature, and average curvature is derivative of force. So integral of derivative of force is given by the force jump. So then what we have to calculate is the jump not in energy, but in the force, and this gives us Campbell length. So this is kind of jump here will give critical force, jump in the force gives us Campbell curvature. So now I come with this work of Filippa. And what we should do is effect of creep corresponds to shift of the position of the jump. So now jump and trapping length depends also on time for the creep, and the same would be for the curvature. So then we have to find it, and that's the result. So these are, well, these are, and these lines are numerical solving position of the jump as a function of velocity and substituted for both these jumps for the pinning force and for the curvature. So what is done, you say that the barrier and the distance between orange line and dashed line is equal to T log T. Then from here you obtain position of the jumps, one here, another here, then you substitute this formula into this and get these lines. And dashed lines are some analytic approximation to different use cases. So these are for different strengths of pinning. So this kappa effect or Lamush parameter is close to onset of strong pinning, some intermediate, and this is rather strong pinning. So here what is plotted is current, magnetization current. That's what measures in the usual relaxation experiment. And this, what is plotted is Campbell curvature. So inverse of it gives Campbell length. Now there are two actually quite surprising results here. One is, well, one not surprising, that current always decays. So creep leads to the reduction of magnetization, system goes closer to equilibrium, that's we all know. But curvature actually here, here, and here grows with time. So it looks like, and if we try to replace the effective potential, then it seems the potential gets more and more curved, and effectively pinning gets stronger and stronger, but it's not the case because current actually decays. So that's one surprising result, that like from behavior of Campbell, you will deduce that effective pinning becomes stronger. And another result is the endpoints here are in this strong pinning approximation. At very low current, we reach equilibrium and magnetization vanishes, but Campbell length, so buffer reversibility line in equilibrium, is not actually infinite. So we have still presence of pinning from Campbell length, even when we don't see any irreversibility. So this is quite surprising results that one gets. So how can one understand it? So why Campbell curvature grow? And there are two reasons. One is simply that trapping distance is growing, because now when I move vortex away from the pin, it can thermally activating jumps to the pin. So creep not only leads to escape, but something which are relatively far away from defect can jump to defect, and this increase trapping distance, or let's say pinning cross section. And another thing is that here, close to the bottom, close to the pinning force actually increases, and this leads to increase of the force. But here at the pinning force decreases, and eventually for large kappa, this effect wins. So one can do some analytic approximation, and this gives this dashed line. Now, why in equilibrium there is Campbell length, and this is because in equilibrium we have such population. So we have not multivariate but single variate population, but we go from one branch to another, and there is change in slope here. There is jump in slope, so there is jump in pinning force even at equilibrium, and that's why Campbell length is finite. Now, how does it agree with experiment? There's not so much studies on creep in the Campbell, and well, I try to motivate people to do it. So this is old, relatively old, well, 2003 work by Ruslan Prozorov. So they prepare system, they cool sample in zero field, then applied field, that's this 0.1, and then they heat the sample and cool the sample, and they see the Campbell length is different in field cooled and zero field cooled. And then they wait, well, both in zero field cooled with temperature and in field cooled. So in field cooled, that's how Campbell length, not so much changing in time. And in zero field, that's how Campbell length is changing. And this orange line is how magnetization changed with time. So usual predate. This is function of temperature. This is BISCO. So at, well, critical magnetization is almost zero at like 20 Kelvin. So creep is very strong. So this is actually data for 2 Kelvin, but one sees quite pronounced creep. Now what one sees here is that Campbell length actually decreases with time. So this is minus sign. So curvature grows, and this is exactly in agreement with our theory. Another puzzling thing is that in the field cool state, there seems to be no any relaxation. So if we come into the field cooled, then what we should do, we have this effective pinning potential, but now we make with temperature decrease, pinning gets stronger and stronger and stronger, and this line gets modified, and now you see jump appears. It's become multivariate, and then if the evolution is like this, then the jump kind of population is this black line, orange, red, orange. So this would be occupation if we are in equilibrium. So the position of the jump is here, whereas in zero field cooled, position of the jumps goes to the endpoint, to this green line. So this would be zero field cooled, Campbell curvature, and orange line is field cooled. So there are different cases possible. The one which I was showing was like this. Then the jumps stays where first time slope become vertical, but one can have situation where there is overall shift of the branch to the left, then the jump is at the end point, or to the right, the jump is also at the end point. And in these two cases, there is actually hysteresis when we, let's say, change temperature cool, then it goes this way, jump is here. Now when we hit, then curve goes back, but the jump stayed the same. And actually Roland found out in some published data by Prozorov group that they have something which looks like hysteresis, and we asked them, okay, can they work it out? And indeed, well, they didn't notice this little hysteresis, but it was really theirs. So now for creep, we also should consider these different cases, and depending, so what we should find position of the jump in this and calculate everything. And there are these three different cases when the jump is at the end. So when the thing goes, let's say, to the right or to the left, everything that the jump is at the end point, and at the end points barriers are small. At the end point barriers actually vanish. So kind of close to here, barriers are small, and the creep is pronounced. But if the jumps goes in the opposite direction, then in the middle, barriers are large, and one doesn't expect to have any creep. So these are this kind of plot as a function of logarithmic temperature. So if it's this scenario where it goes to the right, then curvature goes like this. If it's this scenario goes to the left, curvature goes like this. If it goes in the opposite direction, then first it's horizontal line, so there is no any relaxation, and only at a later stage we merge either this line or this line, depends on which endpoint of the branch will reach the jump. And well, this is a function of logarithm time. In reality, our logarithm scale is limited, so we may never reach this point with the life of universe, like this life of grad student who does measurements. And this may well be in agreement with the data of Prozorov, who didn't observe any relaxation in the field Coulomb effect. So these are conclusions about this Campbell part. I just repeat and emphasize everything which I did here was for radially symmetric pinning potential, and if pinning potential is not radially symmetric, generically why should it be radially symmetric, then all this picture is strongly modified, and we will have about this in the next talk. Thank you very much.
The time is open for questions.
Thank you very much for this talk. So in the first part of your talk, I missed what are the fitting parameters that you use in the fitting experiments.
You mean on the script?
Yeah.
Okay. Okay, so these are original data. And there are two effects of temperature. One effect that simply critical current depends on temperature. So, well, critical current, flux flow depends on temperature, everything depends on temperature. And there is shift simply due to that without any creep. And another thing is that creep produces this rounding. And the question how to disentangle. So then the trick which was done, well, that's just explanation why this is just Ginsburg-Landau, and this is creep. And so that's a formula. So there are critical current, flux flow, resistivity, barrier, and this thermal. So 4 fitting parameters. Well, we can say that it's 4 fitting parameters you can fit elephant, but it's a relatively complicated thing. And another thing is what are these fitted parameters, what you extract, how reasonable they are. And so, it's also rather tricky to fit just with 4 fitting parameters, everything. So this was done in 2 stages. So first, we try to fit linear IV. So we take a straight line, extrapolate high voltage data as a straight line, and then we get critical current and the slope. So in the first stage, we get flux flow and critical current. Then we rescale everything. So measure everything in the units current divided by this critical current, which we extract from fitting to the straight line, and with the flux flow slope fixed. And then we have family of this curve, and here everything is due to creep. And then actually, if you take this parameter, because you get parameter which you should look how they depend on magnetic field, on temperature, and so on, whether you get something completely out of imagination or not. And actually, you get rather reasonable result that critical current, which you extract from fitting straight line, goes like 1 over field in the power, almost like 1 over square root field. So that's what predicted by strong pinning theory, and so on. So the parameter which you extract have rather reasonable behavior. Well, we cannot compare them with independent thing, but they look rather reasonable. So that's actually what was our, well, apart from formula, but we just took the data, and that's analysis which Martin did.
Thank you very much.
One question, maybe around the way the one is concerned on pinning. No more question. Okay, we can select the speaker. Flux is the journey from ETS to Superconducting Transition with arbitrary state potential.
Yeah. Where is this? Where is it done?
What?
Where is it? Is it this one here? Yeah, it's open now.
No, it has to be in the abstract group or the yeah.
I opened it and then it must have disappeared. Okay, sorry for the technical interruption. Okay. Hi. So once again, good morning, and thank you for having organized this nice conference, and thank you to the organizers for having invited me to talk. So today I will continue Dima's talk in another direction. As he mentioned, I mean, vortex spinning is important, of course, for back to superconductors. It determines a lot of phenomenological properties of these materials. But it's not obvious that isotropic defects should be the general case that one should study. And in this work, we are trying to generalize strong pinning to the case of an anisotropic defect and to see what are the results. So to do so, let me first just recap a super brief introduction and stress some points that are more relevant for my talk. So as Dima said, in strong pinning theory, you have an interaction between a single vortex line and a single defect. Now with this defect, we just assume it to be acting on plane, okay? So that's why we model our pinning potential here to be on plane. We have two important quantities, which are, or coordinates, which are the vortex asymptotic position, so how the vortex, where it is far away from the defect on the surface of the sample, and where it is close to the defect, so at the tip. These are R bar and R T. Now, the total vortex energy is quite simple. It's just a sum of these two contributions, one for the potential energy of the tip, which likes to be close to the defect, and at the same time as the elastic contribution coming from deformations of our vortex. So every time you bend the vortex line, you have some elastic energy based. Every time you compress your vortex lattice, you base some elastic energy, and all these effects are effectively included into this term here. Now, you have two variables, but as you can expect, these two variables are related to one another. So anytime you want to minimize your vortex energy to find your stable solution, then you have to solve a force balance equation. And the stable solution is usually the stable configuration of the vortex line is the result of a fight between these two terms. So on the one hand, you have a defect that you want to stay close to at the level of your tip. On the other, you don't want to deform too much, otherwise you have to pay a lot of elastic energy. And this is reflected in this force balance equation. Now, I want to stress the role that the elastic constant plays. Of course, when you have a very stiff vortex or a very large elastic constant, then your vortex energy is very rigid, and the fact that you have a defect is not very important. Okay, you like to be aligned with from top to bottom. Now, when C bar or the elastic constant becomes smaller and the elastic energy is not a large price to pay, then of course you can afford to have larger deformations, and you can afford to bend your tip in order to be closer to the defect. What is interesting is that whenever you have an intermediate regime, then the vortex can be in either configuration. Okay, and this is the bistability that Dima was talking about before, and it's a real signature of strong pinning theory. It's crucial for producing finite observables such as a critical pinning force. Okay, here I have a small cute animation of bistability. Not my greatest artwork, but should prove the point. And then plotting here is the pinning energy for a fixed asymptotic position. So I'm fixing my vortex state far away. And then I'm letting the elastic constant decrease, and they see how the vortex state accommodates. Okay, and I imagine that when the elastic constant is smaller, my vortex will be more flexible, and eventually it will display a bistable behavior. Now let's see if this works. Okay. So you see that the dot here is exactly the vortex tip configuration for fixed asymptotic position. You see that the more soft you get, at some point you have bistable behavior, and then you have a pin solution here, and you have free solution there. So the vortex can either be very close with the tip to the defect or far away. And then another qualitative aspect, which is very important, is that in order for you to connect these two stable solutions, you need to have a region where the vortex tip is unstable. So this is just geometry. In order to have two positive curvature regions connected, you need to have a negative curvature, which I'm here displaying with dotted line. Now, as I say, strong pinning implies bistability. Bistability is a signature of bistability is having unstable regions. So it's very convenient for us if we want to investigate where bistability emerges to look for these unstable regions. They are very simple to find. You just have to, look for the appropriate quantity, and instead of counting local minima, which is quite an expensive operation, you can just take a derivative of your energy and then look where it turns negative. Or if you were able to observe your vortex, you can look and trace it around and see where it skips or where it jumps. And then you know that when it jumps, you have a bistable behavior. Now, this allows us to define a more formal criterion, which goes back to Labush, which in 1D is very simple. You just say that you want your vortex total energy to have negative second derivative somewhere. Okay? And in higher dimensions, or in 2D for our very mundane case, generalizes to the fact that your matrix of second derivatives, or your Hessian, needs to have a negative determinant, okay, in the regions where your vortex is unstable. And now, having developed this nice criterion, which is very mechanical, we will try and apply to the isotropic potential and to the anisotropic potential and see if this is a good tool to explore the physics which comes out. Now, here's another movie. Now I'm showing you, I'm plotting just the curvature of the energy, of the vortex energy, as a function of the tip position. And the colors I'm using are bright for tending to yellowish for large positive curvatures, dark for small positive curvatures, and white for the forbidden regions where you're unstable and your vortex cannot stop. And as we expect, when we lower the elastic constant, my vortex becomes softer, it pays less energy to bend and to become pinned, and therefore the unstable region will grow. Okay? And this is what we see. It's not surprising, everything is isotropic, so you see just a ring which expands, but still it proves a point. Now, we don't expect this to be a general case, obviously, so we would like our theory to be valid also for non-isotropic problems. Now, these are the simplest modifications which you can have to break symmetry. You see, here, for example, we have elongated or stretched the potential, and you see that immediately, because you break the symmetry, you have that the unstable regions are not R2, they're not connected, they don't form a ring. And you see immediately that there is a problem, because when now, well, of course, if you soften C bar, these grow and then eventually merge. But then the problem is that, whereas in this configuration here, there is the inside and the outside of the ring. So we have a pin state, which is close to the defect, which is sharply separated from the free state, which is outside. You have a big forbidden region. When you are in this other scenario here, this is not the case, because you can jump if you cross the white region coming from below, but you can also get to the center of the box by coming from the side, and then you don't have a sharp transition. You're not really allowed to talk about a pin state or a free state. So a little bit of a shaky ground to talk about pin and free states. And the most general case, here we have just an example, is even more problematic yet. Well, here we have just three potential, three defects all summed together, which produce quite a messed up manifold, and you see that the unstable domains grow, they're separated from one another, then they merge, and then at some point they form a ring, and then only when the ring is formed you can finally talk about a pin state and a free state. Okay, only the moment you have a topological separation between the two sets of stable solutions, you can really talk about pin and free state. Now, here my talk takes, this opens up a lot of possibilities, and you can compute a lot of stuff. I presented you two results. One goes in the direction of zooming in of what happens close to the onset of strong pinning. So for these very small unstable regions, which are simply connected, and the other is more of a global result, which holds in general, and which is supposed to show you two, let's say, possible direction in which one can push this analysis. Now, so for the first result, we are looking at the pinning force when we zoom in on this unstable domain. So we have the elastic constant, which is the vortex, which is soft enough for you to have instabilities only at some special point. This will produce a pinning force close by because my vortex jumps, and as Dima showed before, every time your vortex jumps, you have some pinning force. And to zoom in, of course, it's always nice to zoom in. You can do some Taylor expansion. Everything is maybe boring, but it's always very plain. And in this case, when we zoom in on our unstable domain, so this white region is the white region which I was showing you before, where I zoomed in. Then in here, your vortex comes from the left, it turns unstable here. Okay, so your tip is unstable and then it jumps the other side. Similarly, if you come from the right, you turn unstable and then you jump to the left. And this analogous to what Dima was showing with your stable solution disappearing and your vortex jumping. Again, we can relate the tip and the asymptotic positions through some force balance equation. Okay, these equations are just Taylor expansions. They are not meant to be interesting. But what is interesting is that when you go and look for results, so when you want to compute your pinning force due to these kind of unstable domains, then you find something quite interesting. You find that, well, you apply your general formulas, but then you find that your pinning force is actually, so your vortices might come from multiple directions. Okay, you can hit your half-moon region of bistability from different directions, but your result is almost not caring about your angle. So your vortices might come from many directions, but your force is always in the same direction, which is, in a sense, reveals the anisotropy of this equation. So we have an unstable direction on which the vortex is hit, which is not always opposed to the direction of the vortex. And moreover, a little bit more technically, we have that your pinning force exhibits a nucleic exponent. Okay, which one the one could measure in order to prove or disprove our fluids here. Now, the fact that your pinning force is always constant in direction, it's not just strange, but it also produces interesting results because it means that your pinning force, the moment that you put it together with your force balance equation, you have a Lorentz force which pushes your vortices, you have some dissipation. And then your pinning force is not always acting against the velocity. So the power you dissipate is not necessarily very high. You have some angle, which means that your pins are not very efficient at dissipating and at stopping your vortices. So if you had current flowing, depending on the angle, you had a series of these unstable domains in your sample, then you would see that depending on your angle, your critical current will change. Now, on a more qualitative level, what we see here is that the result is very different from the isotropic case, where the pinning force was radial and dissipation was always very good, so your pinning was always very useful. And so we've seen that if you want the fact that the topology of our unstable domain is different, so we don't have a ring anymore, but we have just a simply connected region, changes the physics quite significantly. This brings us to the second the second direction that I would like to hint to, which is how can we know when we have a nice effective pinning center? So how can we know when our unstable domain effectively is a ring? And then inside we have a really pin state, and outside we have a really pin state, and when not. So is there a nice way that we could make sense of this messy potential in a solid way to conclude that we have good pinning centers or not? Now, this is very general because of course your potential can have any possible form. I mean, you also have to change the elastic constant. So you would like to have a recipe which is but based on something which is very strong, like topology. And the idea here is that we want to look at the white region. Okay, so for each value of the elastic constant, you have your unstable region where your vortex tip cannot live. And this unstable domain is a topology, so it might have holes in it, or it might not have holes in it. And we want to find a way to determine whether we have holes or not. And we would like to do it, I mean, finding holes, it's a little bit bothering because it's a global property. I mean, holes are, how do you know if it's a hole or if it's just the other half of the universe and it never closes up? So we would like to use local quantities such as existence of minima and saddles to prove that we have holes. And the game we can try to play is to plot all the minima in our white region, which are these blue dots, to find the saddles in our white region, which are these red crosses. And these points we find just by solving locally. So not too complex equation. And then we like to think that when you have a minima and you have a saddle, to go to another minima, you have to pass through the saddle. Okay, so in a sense, we can transform our unstable domain into a graph. So we can connect the minima and the saddles, and we transform our unstable domain into a graph. We visualize it as a graph. And then you see it's very suggestive because the number of holes inside can be, well, it looks like as if it was directly related to the number of faces of this graph. I know that we're not familiar with graphs here, probably. I was not myself, but this is all very basic. So we're just saying we want some local quantities to characterize our unstable domain. These are stationary points, maximum, minima, saddles. And if we connect them, it's very suggestive because we see that these faces enclose holes. Now, there is a problem. The problem is that nobody tells you how to connect these points. You can connect them in many ways. You see, I mean, there are many possibilities. You can reach the points in many ways. But the cool thing is that all these graphs which you can possibly create are equivalent from a topological point of view. So there is a quantity which all these graphs have in common, which is exactly the number of faces which I was telling you about. So the number of effective peaks. Now, this goes back to Euler. So this is another equation which you encounter on Wikipedia. Maybe you don't have the chance to use very often, at least I never had, but which is super simple and just tells you that if you have a set of edges and vertices, and then you want to connect them, however you connect them, the number of faces will be the same. So if you have a polygon with a number of sides and a number of corners, then this polygon will have a given number of faces, no matter how you connect this, how you combine these objects. And our idea here is to map, vertices to minima. So these blue points are the vertices of our future graph. They are minima. Well, in this case, only one blue point because we only look at white region. Our saddles are edges. And then we can just do a counting and find the number of faces or the number of pinning centers. And you see that, I mean, for the simple case, we have just one minimum, -1 + 1, which is 0, and okay, everything works. You can have disconnected graphs, so separated minima, and then you have to adapt the formula a little bit. You have to replace the one with the number of disconnected units. But then you get -4 + 4, which again is 0, and everything is fine. And you go on, you do the same. Again, here we still don't have a closed island, so effectively we don't have a real pinning center. We don't have a good pinning center. But then if you go further down, if you make the vortex softer, at some point you connect all these points and your graph develops one. Okay. And these are, I want to stress, the number of faces is a really, I mean, it's not a local object. So a hole is not a local object, but we can find it in terms of local objects. And more importantly, these holes, which are very important physical objects because they represent our effective pinning center, so they are directly impacting our capability to slow down these vortices, are in this language a topological invariant of the energy function. And a very simple one, so nothing too complex. So first one should familiarize themselves with these equations a little bit, but it's nothing too strange. And we see that it works quite nice, and the idea is that we could throw some defects, okay, which are even weak, into our material, which are individually not strong enough to form a pinning center, but then they could spontaneously, or gather up by chance. They could just be close to one another. And with this method, by studying the minimum and the maximum of our energy function, we would be able to determine whether these effective pinning centers are good ones or not by simply counting maximum, minimum, and samples. Okay, and I hope I compensated for Dima's extra long talk in my a little bit shorter one. So thank you.
Thank you very much for this nice talk. I have a question regarding one assumption of strong pinning theory, which is that defects are far apart, and your assumption of anisotropic pinning landscape. So how do you combine these two statements?
Yeah, that's a good point. So here, in principle, I mean, I always generate my potential manifold starting from defects. But in principle, we just talk about the potential manifold. And then what is important indeed is that these effective pinning centers are spaced apart. So that these unstable domains which grow, okay, especially when they form proper pinning centers which host pin states, are well separated. And this could be, I mean, you could justify this based on the probability distribution of your defects. So if you start from very weak defects, then you know that clusters which are large enough to host an effective pinning centers should be further away than a certain threshold, I would say. Thanks, it's a good question.
Okay, anything else? Okay, we skip the next stop.
Thank you.
Let's skip the next part.
Gracias para el Zoom. No, gracias para el Zoom.
Want to send our briefing to Alexander. And then the next one is from Engineering.
Ah, sí, sí, sí.
Engineering will be with us from INDEA Nanoscience, Manufacturing, Process, Dynamics, and Stress Diagram Modification Induced by Magnetic and Extraction.
Sí.
Thanks. So good morning, everyone. So I have to say that it's always nice to have some extra time for presentation, although the reason we have this today is not nice at all. So I would say let's all be thankful that we're sitting here today discussing physics while other colleagues are facing a completely different reality. So, yeah. So now back to the science. So as you can see, we're here today we present this work that we have done on the study of vortex dynamics and phase diagram modifications when a superconductor is in presence of different magnetic nanostructures or magnetic templates. So this is a work done in collaboration with all these people that is mentioned here. So let me try to get the pointer again. Right. So in particular, I want to mention Victor and Marina, who are also sitting in this room today, who were the students doing the measurements of, that I will present today. So I think you all, or most of you, would agree that the hybrid systems that can be made by combining a superconductor with a ferromagnetic or magnetic material have shown to be a very useful ground to study many different phenomena, and that is just a few of them. Just to mention that, for instance, the interaction of or the pinning that, let's say, magnetic nanostructures can create on the vortex lattice in the superconductor, the appearance of the main wall superconductivity, also the appearance of triple superconductivity in the case of superconductor and ferromagnet junctions, and not only studying properties of the superconductivity, but the other way around as well. So, like, for instance, inducing different magnetic states in a ferromagnetic material by superconducting nanostructures, or recently the coupling between magnetic skirmions and vortices. So, of course, as I said, this is just a very brief overview, and even there are many, many more works in the literature that you can find on this topic. So this, again, is a way that shows that this type of hybrid systems are very useful to study, for instance, the influence, as we showed today, of geometrical frustration or geometrical constrictions in the system. So just to start, let me remind or show you this result that many of you maybe have seen before. So this is the result that one can obtain in the magnetoresistance when you have a superconductor in presence of, in this case, a magnetic periodic array. So these are these magnetic dots, and on top of that, there is a superconductor, and you can see clearly here the appearance of commensurability effects between the vortex lattice and the magnetic lattice. And this is evidenced here as these dips in the magnetoresistance when the number of vortices is the multiple of the number of pinion sites, in this case is magnetic dots. So besides this, as I said, like expected commensurability effect between these two lattices, in this case there is another effect that plays a role, and that is due to the fact that in a certain temperature region, the system behaves to like what is known as a superconducting wire network. So to explain this, let me just for a moment think that instead of having these dots here, we will have holes that are pierced through the superconductor. So we have now a multiple connected geometry. And as you know, in this case, it is expected that oscillations of the critical current will appear due to the little Parks effect. That is basically a result of the fluxoid quantization. So now you can think that the system is actually this composed by these wires or these stripes of superconductors surrounded by these holes. But this type of effects, these little Park effects, only happens when the coherence length is larger than the width or the effective width of these wires. So going back to the case of the nickel dots, in this paper it was shown that this is the case for temperatures very close to the critical temperature, and that is evidenced here as this square root dependence of the critical field, the upper critical field, as a function of temperature. Right. So if you fit here this square root dependence, then you can extract the coherence lengths at which you would expect this superconducting wire network regime, and it turns out that the width that you can extract by when you met this condition is that that width of the superconducting wires is actually the physical separation between the dots. So this is to show that these oscillations again in the phase diagram are actually a combination of, on one side, the commensurability effect that I mentioned before, and this little Park oscillation. So now let me change to another superconducting hybrid system that has shown to be also very interesting to study many different phenomena, and that is the one that you can make when you proximatize a superconductor to what is known as artificial spin ice system. So yesterday we have seen a talk where actually in this spin ice system, that is a very highly frustrated system, maps of the magnetic charges can be obtained by using the squid on a cantilever. So I will not enter into details of the interesting properties of the system, of the spin ice system on its own, but just to mention that this has been used also as a template to study vortex dynamics now in the presence of these type of pinning potential that can be created by the magnetic charges. In this case, as is shown here by this spin ice is made by these magnetic nanobars. And by changing the magnetic configuration, that can be done easily, let's say, by following different protocols with the magnetic field. So you see here, I don't know if you can clearly see, but at least you really see that there are different arrangements of these positive and negative charges, and that causes a difference in the critical current of the vortices moving on top of this magnetic lattice. So more recently, another type of spin ice system that was studied actually in our group is the one that is formed by now not having magnetic bars, but just like a continuous array of a magnetic material, in this case cobalt, forming this kind of honeycomb array, so this hexagonal structure. So here it's also shown that if you apply a large magnetic field in one of the easy axes of magnetization that is parallel to any of the sides of the hexagon, you can create an ordered state of these magnetic charges that form at the vertices due to the, again, this fulfilling of these ice rules for the magnetic moment in that point. So this is what is shown here. This is a simulation, but it's similar to what you can obtain from MFM images, where you see positive magnetic charges and negative magnetic charges at that. Or here I show only small area, but this is extended in the whole, of course, honeycomb lattice. So now if you look into detail of how this magnetic structure will create a potential for vortices moving now on top of this template, you can see that this potential is asymmetric. So geometrically it's not asymmetric, but the magnetic structure makes it asymmetric. And now we end up with a system that is also has shown to be very interesting. Also, you can imagine that many of you have heard before in the case of vortex lattices, but it's a more general concept. That is when you have particles now, interacting particles moving in an asymmetric potential that are forced or are driven by a symmetric force. This can create a rectification motion of the particles and a net direction for the motion. And that is actually what has been also seen in this case for this superconductor magnetic hybrid system. So here, this is what is shown here. So this is a DC voltage as a function of an AC current. So here the AC current is applied in such a way that vortices will move along the AC direction of the magnetization, as it is sketched here. And you see that, yeah, as a function of the current, then a finite DC voltage appears. So exactly showing that there is voltage rectification, and in this way one can create what is called a flux quantum diode. So the work I want to present today kind of relates to these two topics I just introduced. And there are, in principle, two questions that one can ask. So in the first case of the little Park effect that we have seen in the case of these nickel dots on top of the superconductor, the question is whether the magnetism will have an effect on the little Park's effect. So what I've shown before and explained is basically a geometrical effect. So it's the fact that the dots are separated a certain distance. So to try to understand if magnetism can play a role, what we did is to study now a system where the magnetic array is not made of nickel, but is made of a material that has perpendicular magnetic anisotropy. And that's the case for a multi-layer of cobalt palladium dots arranged again in a periodic lattice. And for the second topic of this voltage rectification, in the case of vortex lattice moving on top of an artificial spin ice system, the question is whether there will be this voltage rectification even if the magnetic structure does not have a long range order. So the potential will be still asymmetric somehow, but not periodic. So for that, we use the same system as before. So it's an ionic field on top of a cobalt honeycomb array. So let me go to the first part of the talk. So as I said, now we are looking at a system that is a superconducting an ionic film on top of an array of dots with a perpendicular magnetization. So as expected, we have again this commensurability effect, clearly seen in these dips in the resistance as a function of field for when there is matching condition between the vortex lattice and the magnetic lattice. So now we go again to the region of interest for this little parts effect, and that is again close to TC. So we have again this square root behavior of the upper critical field with the temperature. And what we do here is we look at this when this condition is met, so that the coherence length is larger than this W, and we extract W. And we can see this width. We can see that actually for the case when the magnetic field is parallel to the magnetic moment of the magnetic dots, the width that we extract is 144 nanometers. That is actually smaller than the separation, the physical separation between the dots. While if we do the same for the other side of this curve, that is for the magnetic field opposite to the magnetization of the dots, then we get again, like in the case of the nickel, that the width is of the order of 200 nanometers. That is the physical separation. So that's a geometrical reason. So here just we are showing here that these oscillations in the critical temperatures can be fitted with this, what is expected for the little Parks effect. So this again, just here what we are showing is that this superconducting wire network regime is extended in the case of the magnetic field parallel to the magnetic moment of the dots. So to try to understand that, we did calculations of the magnetic field profile of the stray field. Actually, when you have this array of out of plane magnetization. So this is what is shown here. So you can see here the dotted line indicates the physical size of the dots, and these are the magnetic field lines. And this is again for the case of perpendicular magnetic anisotropy compared to a case of nanodots now in a vortex state. So don't confuse this vortex with the superconducting vortex. Here we refer to the state of the magnetic moment within the dots. So what we can see from here is that actually this stray field induces a reduction of the effective width between the dots, and that's the reason why when the magnetic field is parallel to the magnetic moment, then we get this smaller width and this larger superconducting wire network regime. And in the case of the field opposite to the magnetic moment, the system the magnetic field tried to compensate the stray fields, and then it behaves more like the case of the nickel dots, where there is no out-of-plane magnetization. So this is summary. It's again like a partial summaries of this first part. I just show you that the boundary of this superconducting wire network regime depends on the relative orientation between the magnetic field and the magnetic moment, and the stray field of the nanodots induces this enlargement of the superconducting wire network, or this the fact that the little Parks effect, showing that the little Parks effect is sensitive to the magnetic state of the nanoarray. So now let me change gears and go to this, at first maybe different topic, but of course there is some relationship. Again, we have a superconducting material interacting with a magnetic structure, and now this is, as I said before, this is a very peculiar, I would say, magnetic structure that has the possibility to change quite easily, I would say, by just changing the history of the magnetic field, the magnetic landscape. So here's this, as I mentioned, is a honeycomb array of cobalts, very thin cobalt, and then on top of that we define this transport bridge made of niobium, where we are going to study the magnetotransport. And here it's just important to indicate that with this configuration it's possible to actually drive the system in such a way that the vortex motion will be either parallel to one of the easy axes of magnetization for this structure or perpendicular to it. So we will study actually both dynamic conditions. So as I said, what we are interested now is to see whether we could have this voltage rectification when we apply an AC driving force, while the magnetic landscape is not a periodic one, but is a disordered one, and that we can do in these two configurations. One is the as-grown state, so that means the as-grown state for the magnetic material. So as you can see here from these MFM pictures, clearly these positive and negative magnetic charges are completely disordered. And the other case is this, what we call this remanent state, that is generated by following this protocol. So you first apply a large magnetic field in one of the easy axes of the lattice, and then remove the field, and then apply the field again but now in one of the hard axes. And therefore you end up with a quite disordered state. So today we just show results for the as-grown state, but similar results are obtained in the other case. So this is what we obtained in this case. So this, as I say, is for the as-grown state, and these are results of the DC voltage as a function of the AC driving force for different temperatures, and these are the two cases that we can study in our geometry. That is one where the vortex motion is parallel to one of the easy axis of magnetization, and the other is when it is when they're moving perpendicular to it. And you will see that the response is quite similar. So this is the conclusion of this slide. Of course, that we can observe this ratchet effect, this voltage rectification for vortices moving in either direction, and on top of a spin-ice structure that is completely disordered. So to understand this, what we did is look at now how the magnetic profiles, the magnetic potentials will look like. So for this, let's say we take this, like here, this positive charge, this positive magnetic charge, and look at possible trajectories for vortices that, as we said, I mean, that since they will be completely disordered on top of the sample, then vortices will cross these charges in actually any direction. So what we can see here is that this is a calculation of the MFM intensity, is that as soon as you move from this horizontal line, then you have already, of course, some asymmetry. This is for one single charge. So if we now look, again, we try to represent with this all possible configurations, but we just look at a few of them. We can do the same for any random orientation arrangement, let's say, of the magnetic charges. So here we see the results of the simulation compared to experimental calculations from the MFM images. So you see this, for instance, if you cross this negative and positive charge, you clearly see, of course, that the potential will be asymmetric, whether the vortex is moving to the right or to the left. So that's expected. That's similar to the case of the other magnetic array. While here, for instance, if we take this possible trajectory across these two negative charges, we see that in this particular case, the potential actually is symmetric in both directions. So these will not contribute to a voltage rectification. However, there are some combinations of even same sign charges that would give also asymmetric potential. So with this, we just show that these local asymmetric pair potentials, mean these magnetic charges, can generate macroscopic effect. So to conclude this second part is just to say that we have observed this vortex ratchet effect independently of the direction of movement of the vortices, and these local asymmetries in the potential generated by these magnetic charges can generate a macroscopic net vortex motion. So with this, I will, this is just a really final summary. These two, as I said, these two topics, let's say, that I presented today. And I think that this is again a demonstration that this hybrid system still, after so long time, they're still very interesting to study properties and dynamics, not, well, in this case of vortices on top of magnetic templates that can be tuned in a very easy way. But you can extrapolate to a more general concept that is interacting particles in the presence of potential that have, for instance, geometrical frustration on some or some geometrical constrictions. So with this, I just want to acknowledge the funding sources that supported this work, and thank you all for your attention.
has taught on the equation of little Parks effect. Because the background of the question would be, you have a change of pinning by this artificial axis, so the shape of the curve will change as well. So the definition of the CT always little Parks oscillation is something quite crucial.
Can you say that? Sorry, I missed the-
How do you define TC for little Parks evaluation in the transition?
Yeah, that's what, let's say, basically what we do. I didn't show here the whole phase diagram, but you will have, I mean, after you recover this square root behavior, the HC2 line is linear. So what we do is we take the extrapolation of that linear part and extract TC from there. So let's say for the sake of the calculation, that I think is good enough, but if, of course, if you want to go to more detailed definition or more strict definition of TC, that is indeed more tricky. But it's true that you have actually both effects competing, not the pinning effect and this little part effect. Yeah.
I have a question regarding your experiment setup on this bus-shaped configuration where you can apply currents in one or the other direction. Can you also apply currents in a mixture of the two, and then get forces that are in an arbitrary direction?
Yeah, in principle, yes, but the geometry is actually optimized, I would say, for the parallel and perpendicular. And of course, that could be done if you create your lattice rotated, so that could be another way. But in the sense that, you know, we have these wide contacts for the current, right? So in principle, like yeah, you could, let's say, apply current here and here, but then it would be a very inhomogeneous current distribution. So that would, in this geometry, would be much more complicated, I would say, but it is indeed possible. Yeah. But yeah, what we show here is that when you have this disordered state, actually doesn't matter for the rectification, at least doesn't matter since which direction the vortices are moving. So it's
Thank you. What was here? Comment? Okay, we thanks again the speaker. And the last one is by Aragon from NTI Dresden, Germany, and Bariloche, Argentina. On the side of this disorder, with the only part, what the matter with wrong instruction, the name of Germany are open.
Good morning, everyone. Can you hear me? Thanks to the organizers for the invitation. And today I will talk about disordered hyperioniform vortex matter with rounding distortions in iron selenium and low fields. The hyperioniformity is a property present in many interactive object systems, and we use it to classify the vortex matter located in type 2 superconductors. First of all, I want to say that the fingerprint of a hyperuniform system is the algebraic decay of the structure factors when Q tends to 0. And here, for example, I present how this factor stratum looks like in the host media, Bismuth 2212. And we can see in this part we study how this hyperuniformity is modified by the disorder of the pinning centers in the host media. For example, we study Bristen, electron irradiated and correlated disorder pinning centers created by heavy ion irradiated. And we can see in this part that even when we have a very disordered lattice, for example, in the correlated disorder by columnar defects, we can observe the algebraic decay in every angularly averaged factor structure that I showed here. In this part, the red line represents this decay. And if we see how the exponent depends on the applied magnetic field, we can see that it still remains near to 1. And this tells us that this class of systems, all of them are class 2 hyperuniform. And this is very interesting because we can say that there is an order hidden inside the disorder. And even more, I can show you here that some analytical predictions for phases of 3D vortex in superconductors has the same class of hyperuniformity, even when they are very disordered, like the liquid. And now we wonder what happens if we change the electronic and elastic properties of the medium and how this affects the hyperuniform class in the vortex matter. So we use a different host media, the iron selenium superconductor. This material has a critical temperature near to 9 kelvins and structural transitions near to 90 Kelvin. All the samples were grown in Bariloche and they are very similar to this one. I will show you here. And this material has a nematic electronic order that implies a broken symmetry in the XY plane. So this is related with the elliptic halo shape of the vortices that was measured by STM. And when you increase the applied field, you can see a transition from a hexagonal vortex lattice to a square one. And as I told you before, when we can study the hyperuniformity, we need to go to the Q tends to 0. So we need to see big areas with big quantity of vortices. So in order to do that, we use the magnetic decoration technique. In this experiment, we have a sample in a chamber, and after a field cooling, we evaporate iron particles. These particles travel through the chamber, they crashes between them, and then tends to form clusters of iron particles. These particles stay in the chamber, and they are attracted by the magnetic force induced by the spatial modulation of the local magnetic of the vortices. And they glue to the surface sample. So when we turn off the applied field and when we warm up the sample, these particles still glue to the surface. And we can go to, for example, and scan in electron microscope and obtain pictures like this. In this one, for example, with white dots, we can see the clusters of iron that decorate the vortices positions during the experiment. In this one, I showed you one picture obtained at 5 Gauss and 2.3 Kelvin. Always we work in the part of low fields. So we can obtain in this experiment, for example, more than 30,000 vortices in only one picture in a snapshot. And in this part, I showed you the Telomere Triangulation. And as we can see, in this part, with salmon dots, we highlighted the non-six-fold vortices, and they are the defects of this lattice, and the density of these defects are the 50%. And we have the standard deviation of the first neighbor distance, A0, of 22%. That these values are very nominal for decoration in the low fields regime. But you could see how is the distribution of the angles, the inner angles in the triangles obtained by the triangulation. We can see that there is a non-symmetric distribution, and it's very, very particular because we can decompose this in 3 Gaussian distributions centered in 55, 17, and 16. degrees, and this distribution corresponds to oblique fluctuations. So in this part, we can say that we have a disordered lattice that has domains with hexagonal symmetry and another one with oblique symmetry. So this part is very related to that we see in the structure factor. Here I can show you that this lattice is very polycrystalline because we have white spots in the structure factor, and if we study and we think in the mixture of these domains, we can think that we can pass from a hexagonal perfect one to an oblique one if we stretch this hexagon in one of the directions of the primitive vectors. So in this case, we have two different orientation of the oblique lattice, the red one and the blue one. And if we analyze this structure factor, we can see in the angularly average structure factor in the highlighted with white regions that we have peaks. For example, pay attention in the blue one, and we can see that in this horizontal section, that is the one, we can see that Q1 is bigger than Q2 and Q3, and we have a local maximum corresponding in that area, and the other two spots are in this one, in the 2 and the 3 section, and we can highlight it with blue circles, and if we do this for the red one spot, we can see again that these two domains are present in this structure factor. So we can say that this is a polycrystalline oblique structure. What happened with the hyperuniformity? To observe what happened with the property, we angularly average all the structure factor in all 4 sections, and we can see the algebraic decay with an exponent that is less than 1 and bigger than 0. So this is a class 3 hyperuniform structure that is very strange. And if we analyze again the structure factor in sections, we can see that all of these curves follows the same tendency. So we can say that this is a isotropically class 3 hyperuniform structure, and I said before that it's very strange because always we see a class 2 hyperuniform systems. So what happened? Because before I said you that if you change the centers, the class of hyperuniformity doesn't change. So what happened here is that the interaction between vortices change. In this case, if we reproduce by simulations the structure that we obtain by experiments, we must add a term that comes from the magnetoelastic effect that these samples have. And this term looks like this without power, and it's related with this parameter. It's determined by this parameter. This parameter has all the information about the magnetoelastic effect. And if we do Langevin dynamic simulations, we have to use this new interaction or this modified interaction. And if we see how it looks, we can see that in some parts, in the horizontal and in the vertical line, this force is repulsive, but in the diagonal, it's attractive. So if we do the simulation, we can obtain this kind of structures. The values, for example, of the density of the text and the standard value of the first neighbor distance, it's the same of very similar to the experimental one. And if we again calculate the structure factor, we can see a very similar pattern. And for example, if we average again angularly this structure factor, we can see that the simulation again follows the same decay. So this is a very nice test result for us, because we can say now that this hyperuniformity property it's very sensitive to change in the interaction between vortices. So the conclusions are that the vortex extractor in iron selenium at low density is disordered, and even more, we have a mixture between oblique lattices and hexagonal lattice. And if we reproduce this distortion, we can use the magnetic elastic effect, introduce a weak anisotropical long-range exotherm in the vortex interaction. And it's very important, because if we didn't do this, we obtain always the same hyperuniform hexagonal lattice. And the polycrystalline vortex matter in iron selenium is a class 3 hyperuniform system, and even more, this is a high isotropicality property. And well, for me, that's all. Thank you.
Question? Comment?
Well, thanks to the presence of this microphone. I was just wondering, this magnetic term that you mentioned, that would depend on the magnetic field somehow, or if you focus on it or very low field, right? But we expect that it can vary. Of course, we have less work in one field, but we have other fields.
I don't think I understand well your question. Could you repeat?
Yeah, it's basically some of the last term that you have mentioned, that depends on the water separation again, or the magnetic field, so how this will change when the presence increases. So this analysis for fire and
Yes, I think it is in this case. It all depends on the magnetic field, because this parameter eta that describes this effect only depends by the dependency of the critical temperature in terms of depression. So in the magnetic field, it doesn't play a role in this. Maybe this term changes when you change the applied field, but by this term, the London term, not the magnetic elastic.
I have a question regarding the power alpha that you have. Does it depend on the value of theta that you choose in this magnetoelastic property?
This value? This one?
Yes. If you change theta, does it change alpha? You have this power of 0.29.
Yes.
Experiment. And the simulation seems to have almost exactly the same power.
Yes.
Now the question is, does it depend on the value of theta that you chose?
Yes. Yes, and we estimate this theta by experimental values to do the simulation as realistic as possible.
Thank you very much. Now, maybe I missed that, but maybe you can correct me, please. So the magnetoelastic coupling comes because of the symmetry of the crystal lattice, right? Or
yes, it's the coupling between the elastic properties of the system and the structural properties.
Okay, because this is a four-fold mean square. Right?
Yes. This lower, yes.
Okay. Now, this material is nematic, right? Do you think you can? How would that influence?
Well, influence a lot. Yes, because this nematicity is that change of the panoramic, and it allows the vortices to interact different in this material, because you have another characteristic or another features in this medium. And in this case, we must add this term, Because if you didn't do this, you always obtain the hexagonal one, the hexagonal one. We think that it's very important because if you want only this term and no more terms, you can reproduce the main result.
But there is no magneticity there.
No.
Okay.
Yes, just the magnetization.
Did you do what happens? I mean, your crystal has domains, multi-domains. Would you think all that would change if your crystals see?
Well, we don't know anything about it yet. But thank you for the question.
Thank you.
More questions? And now, two things at the same time. We are going to send our best wishes to Professor Dobrovolsky and to thank all the speakers in the session.
Yeah. Maybe please, now you can remove your posters. Okay. Thank you.
Hi, Vladimir. Are you there?
Can you hear me?
Yes, I can. Hi.
Hi. Buenos dias still.
Well said, well said. How are you doing?
And now I will start video. 1 second.
Yeah, perfect.
Yeah, it's a question whether you can see me.
Yeah, we can see you, yeah.
Good.
So you can try sharing your screen if you want.
Yeah, we will try now, but shall I call you Juan Antonio or you are Juan? Jose Antonio.
Yes, Jose Antonio, yes.
Jose Antonio, okay, very nice to get acquainted. Good. Now, I have one general question, and this refers to the session which will be.
Yeah.
If somebody makes a presentation, I can hear it and I can see it perfectly. Okay?
Hi.
But if there is some discussion in the audience, okay, I can hear it only through the microphone of the speaker. You see?
Yeah.
And therefore the quality of this sound is very low.
Yeah, we have noticed.
If somebody makes a question online, it's perfect. I can hear you.
Okay.
When you are talking to me, I can hear you in spite of the fact that you wear a mask.
Yeah, we have noticed. We have increased a little bit the volume of the microphone.
But if somebody from the audience wants to put a question, it's very natural at a conference.
Yeah.
Please take care that he or she will use a microphone.
Okay.
It is not sufficient when somebody from the 5th row simply says something. If I would have been at your place, it's no problem. But I am unfortunately very far from sunny Madrid. Is there sun in Madrid or not?
No, it's not sunny.
Not sunny. Nevertheless, we will make it vivid. Okay. So could you please take care of this?
Okay, yeah, so
I think you have some wearable microphone. If not, simply ask the person approach this microphone. It's very normal, it's very natural.
Okay, so we have tried increasing the volume of the microphones, and if not, we will.
Yeah, no, but I understand. I explain you the reason. Yeah. There is some acoustics in the room. Are you at Universitat Autónoma now?
That's the other solution. Yeah, so the other solution is that I can repeat the question for you.
It's very good solution. Yes, I agree with that. I agree with that. But my problem is that
Yeah, sometimes if they don't approach the mic. Yeah.
Good. Jose Antonio, they speak and I hear a lot of waves, both direct to the microphone and also reflected from the walls. In fact, you have great acoustics and you can arrange some concerts in that hall if you like.
What? When they speak, you can mute your mic. You do this?
Sorry?
When the presenters online.
Yeah.
We will mute the microphone.
No. This is open and the sound goes from here.
Okay, that's maybe he is complaining about it because it's a lot of surrounding sound.
In. We know, but we have a kind of problems trying to direct the sound directly from the microphone to the computer. So we tried doing this, and it's probably one of the.
Okay. So you mean that
when we're setting this up, we tried that to try to direct the sound that comes from the microphone to the computer. Yeah. But it was really messy. It didn't have it coupled sometimes to the speaker, so we ended up doing this because we felt that it was safer.
No good. So thank you very much. Now let us try to open my presentation. I will make a couple of steps and you will look what you can see. Here I have a German description. So first I will share my screen. Good. Then I must find whether my
Okay, let's see.
One second.
Mm-hmm.
It must be what that.
Yeah.
I must close this. No. Now I will open this. And I will try
I think we have it downloaded here.
I will find it. 1 second.
Yeah, it's
There
here.
are many. Oh,
No,
no.
check it now.
I don't know why. Here I see. Yeah. So now I will go to the first.
Yeah, we can see it.
So it's interesting to me what you can see. This is now not a show mode. Okay, I will click on show mode. Okay.
Okay, yeah, perfect.
What can you see, Jose Antonio?
No, we can see the first slide, the introduction.
Yes. Then I will go in a fast mode through all slides, simply in order to be sure. Please look at my screen, and now there will be a greeting which is still not appropriate, but I am very sorry for that.
Buenas tardes.
But after 12, it will be okay.
Okay. Double line, yeah. Yeah. Looks good, yeah.
And the very last can be already addressed to you, Jose Antonio. Read, please.
No, thank you. Muchas gracias a ti.
Okay. Okay, de nada. Okay, now I will escape.
Yeah.
But I am still related to it, and I must find, this is very important, it's in another place. I must stop my sharing.
Yeah, now you have stopped. Yeah, perfect.
When I have stopped it, can you now see me? Yes, good.
Yes.
And again, only 30 seconds, I will again see where it is. I must find it.
Okay, yes.
I must.
You're not sharing?
I must share it again, and I must turn on the presentation mode.
Yeah.
Yeah, wonderful. And now perfect. I can stop it. Stop it. Good.
Okay,
so,
perfect.
Jose Antonio, thank you very much for your care.
Thank you.
What happened yesterday, I do not know, but all links which I received from Iran were not working.
Yeah, don't worry.
I do not know whether it's my fault, but I cannot influence what happens at Universitat Autónoma de Madrid.
Yeah, don't worry. It's no problem.
Very good. But I think now it's still, we are ahead of time, and in the morning session, I observed that there was some change in the program. True?
What,
in
sorry?
the morning session, there was some change in the program.
Yeah, Alexander Drobolowski didn't present.
Yeah, okay, and you changed it. But do you know whether all the speakers in this session are available?
On this next session, yeah, I think that, well, Reader Boss, I think he had a problem and he's presenting, but he's the speaker after you. So all the rest of the speakers that are before you
you're very good. Very good. No good. At any case, if you see that I am speaking too long, you may stop me without any hesitation. So it's no problem.
No, I think there is enough time. So yeah.
No, in any case, I would not like to use some spare time because everyone should have the same conditions. Good.
Okay.
Good. So, Jose Antonio, how are you with COVID?
What?
In the time of COVID, in the pandemic,
How's the pandemic going here?
how are you personally?
I'm good.
Good.
Yeah, making sure that everything runs smoothly.
Yeah. No good. No understand. I understand. I hope we will still have an occasion to talk to you on once.
Yeah.
But I would like to wish you good health.
Thank you. I wish the same for
And
you.
Successes.
Thank you very much. See you in a bit.
Yeah, see you a bit later. Good.
Bye.
Okay.
Good morning. Welcome back to this session number 9, low dimensional superconductivity. I'm José Valdovi from the Small University of Valencia, and I have the pleasure of chairing this session. Our first speaker is Alexandre Gautrin from the University of Bordeaux, who will talk about the influence of a circular polarized radiation on his spontaneous current generation in semiconductor. The floor is yours.
What is it? Thank you. Well, first of all, I would like to thank the organizer for possibility to participate in this nice workshop, and I am really very glad because for me it's the first normal talk for more than two years that I'm here. In my talk, I would like to speak about the possibility to use circular polarized light to influence the magnetic states or current carrying states in superconductor. And this work has been done in collaboration with my colleague, Mikhail Kroitor, who is an expert in numerical modeling, and Brian Muniz, who is an expert in nanophotonics. First of all, outline of my talk. I will first introduce direct and inverse Faraday effect, and then we'll speak about what we can expect to see in superconductor. And after, I will present our analysis in the framework of time-dependent input out question. And finally, I will demonstrate that combining inverse Faraday effect and the Keeble-Zurich effect, which is related to the strong fluctuation regime during the very fast cooling, we can generate current carrying states in nanoscopic rings without external applied magnetic field. So light will serve some sort as a source of the magnetism here. Well, the question, the general question that I will address, can we generate current solely by light in superconductor? But let's start with the Faraday effect, which has been discovered a long time ago by Michael Faraday, and he demonstrated that if you have linear polarized light, and we apply magnetic field along the direction of the propagation of this light, the plane of the polarization will turn depending on the path on the magnetic field. And it is a well-known effect which is used for magneto-optics and so a lot of application. But also it has been noted and firstly by Lev Kitaevsky that in fact if we have circular polarized light, in such case the circular polarized light D is here. What is the point? Should I use this one? There are no all style as yesterday. Okay. And it is proportional to the vector product of the complex amplitude of the light. And for linear polarized light, it's 0, but for circular polarized light, radiation creates magnetic moment. So it's called inverse Faraday effect. And this effect has been observed in magnetic instrument and also in some magnetic metals. And here it's result of the experiment of, I guess, the group of Kim and Kirill. They applied to the magnetic material the circular polarized light, short pulse, and this short pulse, due to this magnetic moment generated by the light, create some deviation of the magnetization from the equilibrium state. And then when light is switched off, the magnetic moment start to precess going to the equilibrium state, and this precession is just clearly observed in this experiment. Now the question is what we can expect in superconductor. And to address this question, we started from the simple model. We have a small superconducting disk, which is irradiated by the circular polarized light, and we calculated if it's possible to generate a current. And it's occurred to be very important here to take into account in the time-dependent Newton-Landau equation that relaxation time normally it's considered as a real one, but in fact it has some small complex component. And this complex component, in fact, is responsible. It's just a reflection of the whole electron asymmetry. In other words, some dispersion on the Fermi energy. And namely, this complex constant produce Hall effect in superconductor. To explain the observation of the Hall effect, you need to take into account the complex contribution to the. And now, if you write this equation and take into account that if we have electric field of the circular polarized radiation, it's also create vector potential, and no, it's vector potential which ends in the equation for the parameter we take into account this, we put this vector potential, and we calculated current, and indeed we observed that this current appear in the disk. It's zero at the center of the disk and increase when we go to the border of the disk. But unfortunately, the estimate that we provided, they show that this current is pretty small and corresponding magnetic moment which it's generated by it's not large. And for example, just to provide some idea for the disk of the micrometer radius and for electric field or intensity of the radiation, which not destroy superconductivity due to heating effect, because always all this effect is proportional to the intensity, but when we increase intensity, heating will destroy superconductivity. So we should optimize the condition. And when, for example, the increase of the temperature is only several %, so superconductivity is not destroyed, we obtain for this small superconducting disk magnetic moment of the order of 1,000 Bohr magnet. So it's measurable. It's measurable. You can measure with nanospeed with vacancy in diamond, but it's pretty small. It's not large effect. Then we decided to find the way to increase, nevertheless, this phenomenon to generate current in more, I guess, more simple way. And we have addressed the possibility to go through the transition very quickly and to use so-called Thibault-Zurich mechanism. Thibault-Zurich mechanism has been proposed by Thibault to explain the creation of different cosmological objects due to early stage of the cooling of our universe. And it was some sort of the fluctuation where after that were frozen. And Zurich proposed to generalize this phenomenon to condensed matter. And so when we go through the phase transition temperature, there are a lot of fluctuation, and this fluctuation creates a lot of defect. And in superconductors, this defect are known as vortex-antivortex pair. So when we quench superconductor through the transition temperature, a lot of vortex-antivortex pair are generated, but after that they are merged to each other and in uniform superconducting states emerge. And in fact, this Thibault-Zurich effect has been observed in superconductor due to the very short heating pulse by laser. And for example, I would like to mention the first experiment in group of brain Lunis. They used tightly focused laser beam to hit locally superconductor nearby a vortex, and vortex has been attracted to this region because its energy was smaller. And so, like that, you can drag a vortex with a laser beam, and for example, you may use a laser beam to write something. Here, it was initial disordered system of vortices, but after laser beam, it has been written AV, abricose vortex. And we send this as a Christmas card for abricose. This time it was last. Well, another possibility to use this heating effect is just apply very short laser pulse to overheat superconductor above critical temperature, and then provoke a fast quench. And during this fast quench, a lot of vortex anti-vortex pair appear. It's magneto-optical images. And if we optimize the condition, we can generate only the single vortex anti-vortex pair by laser beam. But nevertheless, it's always vortex anti-vortex. You cannot discriminate with that. So the idea was if we can use circular polarized radiation to favor some polarity of the current carrying state. And we started with a simple model, superconducting, small superconducting ring irradiated by circular polarized radiation, and also it's subject to fast quench. So we consider this situation, and the idea was that during the fast quench, all type of the fluctuation, and for this little parts geometry, the fluctuation are simply the state with a higher orbital number. The ground state is L equals 0 orbital number, uniform superconductivity. But all excited states, it's N equal 1 plus minus, and it corresponds to the current circulating in one direction or in another direction. So it's carrying states. But if you cool down slowly, in such case only ground state is realized. And so we looked on this problem once again using the time-dependent input Landau equation. But to describe people to detect, we need to introduce here some stochastic force, which describe thermal fluctuation here. And then we have calculated the final state of the system. And the setup was as following. So we have more or less, let's start, continuous circular polarized radiation and very quick cooling of the superconductor. And here, first I would like to show some example of the evolution of this system. Here it is a temperature, very fast decrease of the temperature, quench of the temperature, and here 0 corresponds to Tc. And so you see when it is a time. And we see when the temperature reach Tc, shortly after superconductivity appear. Here, this curve corresponds to the amplitude of the different harmonics. So a lot of harmonics is generated, and it is namely the region of the Pibble-Zurich effect. And then temperature is practically constant here, and we switch off the circular polarized radiation here at the time 75, and the time is measured in the relaxation time entering this input Landau equation. So pretty short now, several picoseconds. And then we see the remaining state here. It is only one harmonics, but it may be 0 harmonics or n equal +1 plus n equal -1. And I would like to stress that these states are metastable. So if you generate current frame state, it will exist for a long time. It will not transform to n equals 0. So if we apply this, let's say, fast range, we can generate different states. And now it is stochastic which work. And it was realized approximately 500 noise realization, 500 cooling cycle to see what happens. And here are the results. Here are the results, probably. Okay, I will show first. Here are the results. Depending on the intensity, that's dimensionless of the radiation, you may see the probability to realize current carrying states -1 you see, it's pretty small in the absence of the radiation, but it's around several percent. So if we have no radiation, we can nevertheless generate the state equal n plus 1 and n minus 1, but with equal probability. But when we apply this radiation, the probability for n minus states dramatically increase and reach here practically 80%. But the probability to realize here the states n equal 1, you see, is drops practically to 0. So in fact, it means that in this regime here, we can generate with 80% probability n equal minus 1 current carrying states. And naturally, for probability, remaining probability 20%, it will be ground state with no current. But we see that definitely chirality of the radiation, is very important, and it's just present here. It's more precise graph. Here, probability to have 0 ground states, n equals 0 uniform ground states, is decreased when the increase of the intensity. And here you see the probability of n equal 1 states with good, in some sense, polarity is strongly increased. But here the probability of the states with opposite polarity, which is very small, because in fact, please note that the scale is very different. So it's, the probability is practically 0. So, like that, we can generate the current carrying state with direction controlled by the chirality of the light. But also we may ask, it starts to increase, but after that, probability drops. What happens here? And in fact, the reason is that when we have high intensity of the radiation, this radiation works as a pair breaking effect. So, in fact, radiation destroys superconductivity itself. And in this high amplitude region, we have different mechanism of the superconductivity destruction, and it corresponds to this curve. When we have here large amplitude of the radiation, and you see the system is pulled down to TC, to the critical temperature, but superconductivity did not appear, because here we have the external radiation which serves as a pair breaking. And we need to wait to the time equal here to 75 approximately, when we switch off the radiation. So here it's mechanism of superconductivity generation when we suddenly switch off the circular polarized light. So it's not Kibble-Zurich effect. It's not Kibble-Zurich effect, because thermal effects are play no roles here. Once again, here temperature is practically equal to below TC, but with radiation, superconductivity cannot appear. And it starts to appear only once we switch off the radiation. So it's very different mechanism, which also we'll study right now, and it's possible to use to optimize and to increase, in fact, the possibility of generation of current carrying states. Well, so to observe now how we can expect to observe this effect. First of all, we should have a good thermal contact, because naturally high radiation is favorable for this generation mechanism, but provoke heating. And in fact, we performed some estimate that for maximum radiation we need to generate vortices. If we have a niobium ring on the sapphire substrate, we can arrange the increase of the temperature of the order of several percent of degree. So it's quite okay for heating. But important ingredient here, as I already told, it is the imaginary part of relaxation constant. And in general, this imaginary part, comparing to the real one, has a factor, small factor, Tc over Fermi energy. So it's pretty small. And we performed our calculation for this parameter approximately 0.1. So we need to work with high Tc superconductor. This is ratio more or less important. Or already mentioned today, iron selenium compound. In this compound, Tc is of the order of 30% of the Fermi energy. So it seems to be very good candidate. So this is the but once again, to check if it is appropriate material, we may look on the whole effect, because the whole effect is governed by the same constant. If we have a well-pronounced whole effect, so this superconductor could be a good candidate. This phenomenon. And then when we generate this carbon carrying state, naturally, after that we can switch off all radiation and temperature constant, and it will remain due to metastability of this state. And we can easily measure this magnetic moment. Now ring is speed of all this vacancy time. So, conclusion. Inverse Faraday effect in superconductor combining with people Zurich mechanism or another mechanism, analytical mechanism of the radiation modulation, open a way to all optical generation of the current carrying state. So hierarchy of the radiation can select the direction of the current. And naturally, for example, you can apply the circular polarized radiation with one polarity, generate current, then apply also the laser pulse with high intensity with opposite polarity, and to switch the direction of the current to the opposite one. Okay, so thank you for your attention.
Now the session is open for discussion.
Your parameter gamma, as you said, is related to the particle holes in cubic. This imaginary part of relaxation.
You mean imaginary part?
Yes.
Yeah, it's related, in fact, with the dispersion of the electron spectrum at the Fermi energy.
Right. So I can relate that to the curvature, right? So you can relate that directly to the curvature of the dispersion.
Yes. All effects are proportional.
Right. So then I'm just curious why is it PC upon df, which matters, because if the curvature is large, I can imagine a free particle model this will be directly related to PC upon Fermi energy. But if we have a local curvature because of many body effects.
Yeah, but normally what counts is the relation of Tc. If Tc over Fermi energy is large, so you expect a large dispersion.
Okay, thank you.
So it's simple.
And could you go to slide 16? I have one question about the experiments. Could you go to slide number 16? to slide number 16. So when you plot this temperature as a function of time, the time is in picosecond scale.
16, this one.
Right, yes, yes. So you show this dashed curve which depicts temperature as a function of time. And this temperature it's in a highly non-equilibrium situation. So what exactly, how has this temperature been measured? Is it the electronic temperature or the phononic temperature or is it all thermalized?
It's electronic.
Okay, so it's okay. Yeah. Thank you.
So we're looking on the project.
Thank you.
One question there.
What are typical values for gamma parameter if it is fitted by Hall effect? Do you know for some systematic study for fitting of experimental data? For example, 10 to minus 2 for cuprates, 10 to minus 3 for niobium, or something like this.
Unfortunately, I don't know exact value because it's rather contradictory. Some sample effect was observed and some not, so it's not let's say well established. But I guess this iron selenide compound seems to be very promising due to huge TCO thermal integration.
Another one there.
Will the pairing symmetry of the superconductor have any effect on this?
Our approach is so general, it's time dependent on our question. So we obtain the same equation for S wave, for P wave, but
the nodal was not.
naively we can expect that this parameter, imaginary part, will be higher in P waves, but it's just some guess.
Because in that case, it will help you because you say gamma, increasing gamma will increase it.
Yeah, so the problem, the reason, in fact, why we use this time-dependent one-hour question, because analytical, microscopical approach is extremely difficult for this problem. It's, in fact, nobody managed to solve this question. And also, I would like to say that the time-dependent Giesler-Blandner equation has been strictly derived only for some special case. When we have magnetic impurity, for example, have more or less gapless superconductivity. That's why I guess that D-wave superconductivity will be better described by this time-dependent Giesler-Blandner equation. But in fact, we should consider our result as just some indication that this effect could exist. So, inverse Faraday effect, the superconductor exists, and it's related with this imaginary part. But all others, so please consider like qualitative approach.
Just one more short question, Vincent. So, does this, when you are calling it as a current carrying, you don't mean a finite momentum superconductor, right?
Sorry?
So, what will happen if you have a finite momentum superconductor?
What we
Like
have?
a FFLO or a PTO?
What we have?
So, a finite momentum Cooper pairs, like a FFLO state.
Speed?
Yeah, you have finite moment.
So, like an
Use
FFLO state.
magnetic superconductor.
No, and an FFLO state.
What's it?
FFLO. Full FFLO.
So, why FFLO state will appreciate?
No, I'm saying, will it enhance this effect?
Oh. First, let's find superconductor when we observe for sure FFLO. It's very rare.
Because FEC is supposed to have some.
No, it's nothing to do with FFLO. I guess it's even difficult to find something which is good for this, let's say, imaginary coefficient. But FFLO Factor FFLO has been observed probably only in low-dimensional organic superconductors. That's it.
There are some experimental evidences that in this high magnetic field you can have.
No, experiment. For many years I worked on it a lot. And the only reliable experiment which indicates it's like superconductor. Because you see, to generate FFLO, you need to apply external magnetic field, which is very large, near the paramagnetic limit. And to do this and not destroy superconductivity, you should apply magnetic field along the plane to eliminate orbital effect. Otherwise, orbital effect will kill superconductor. And then here you should apply huge magnetic field, and after that we will look on some very small magnetization effect.
Okay. Let's thank the speaker again. And the next speaker is Alexei Kalapukov from Oxford University, who will talk about proving conventional superconductivity in the La aluminum oxide and superconducting oxide interface using transport in nanowires.
Good. Do you hear me? Very nice to be here, and thanks for the kind introduction for Gina. And I also very much thanks for inviting me here. As I want to be clear, it's my first trip in 2 years, and what I missed most is actually meeting new people and exchanging new ideas. So it's really nice to be here and be in real life. So. Right, so what I'm going to talk today, I will bring you to changing gears a little bit, and I will speak about a little bit exotic system. Let me see if I can find the pointer here. It's in Spanish. I can guess. I think it's this one, yeah? Yeah, good guess. And I'll try to convince you. This is a system that is not very much discussed in the superconducting community, actually, but it's been quite a hot topic. And so this is a system in the oxide interface. And what I'm trying to do today is to convince you that we do see some indications of an unconventional superconducting barrier system. So this work was done in a project supported by Quantera. It was the first call that finished last year. And that was very ambitious goal of this project to actually try to realize or show the possibility of the system for quantum technologies, while still far away from that. But this was like a large collaboration. So the work was mainly done by my former postdoc, Kanendra Singh, who's now moved to Barcelona. And also I would like to acknowledge a collaboration to Andrei Kaviglia group in the University of Delft for providing the samples. And also finally the work by theory group in Salerno, CNR spin by Roberto, Mario, and the postdoc Claudio, who actually came out with the idea of how to explain the data, and that's what will come in the end. Right, so let me just start short introducing the system that I'm going to discuss today. So the interface between lanthanum aluminate strontium titanate, it was discovered actually already quite a long time ago, almost 20 years, but still remains quite a hot topic. Well, it's actually quite simple system. You just need to deposit a very thin lanthanum aluminate film on top of the strontium titanate substrate. You need just few atomic unit cell layers, actually exactly 4 unit cell or more. And then what happens is there is an electron gas that is formed at the interface on the side of the strontium titanate substrate. With a thickness of only a few nanometers. So despite that both materials are wide bandgap insulators, you get this metallic interface. So it became very hot topic, as I said, and it's actually turned out to be a very rich system. It's a very busy slide. I'm not going to do all the details and panels here, just to impress you by the number of works and the discoveries in this material system. But what is relevant to my talk today is actually the system is superconducting. There's some claims about it. It's two-dimensional superconductor. It's still discussed a lot. The critical temperature is quite low, 0.3 Kelvin, which corresponds to the pulse transient titanate, so it's not surprising. But also it has, due to the interface symmetry breaking, it has very strong spin orbit coupling that actually the energy exceeds by several times the superconducting gap. And it has a quite complicated multi-orbital physics. So then the relevant question appears, discussing in the community a lot. So what happens to the superconductivity in the presence of the specialist multi-band occupation that we can tune with a gate? So is there any kind of possibility of the realization of an unconventional superconducting period in the system? Yeah? Now, before going into superconductivity, we need to clearly understand the band structure of the system, which is, as I said, quite complicated. So in the presence of the interfacial quantum belt, there is a band inversion from the pulse transient titanate. So when you start population the electric energy bands in this interface system, you start first with a light mass, small energy density, small density of states bands in d, x, y orbitals on the transient titanate. And after you continue the population, then you enter the second band, which has a high density of states, high effective mass. Due to spin orbit coupling, there is also a small gap opens between these two bands that some people treat as a Lifshitz transition. So there is no direct indication that there is actually Lifshitz transition. And it has quite a special dispersion of bands in both outplane and inplane. So now, when it comes to the superconductivity, in the very beginning, it was clear that the super concept of the superconducting transition corresponds to the beginning of the occupation of the heavy effective mass band, which is quite obvious or expected because it has high density of states. And if you look in first experiments in the tandem spectroscopy, or for example, the slit microscope experiments, they all basically indicated quite simple scenario that it's one band superconductivity, S wave. So nothing really special happening here, looks like. But then more recent experiments on the system where you can actually have inversion of bands on different orientation of the substrate, where you can first actually populate the heavy mass band and then you go into the light mass band, light effective mass band. They showed actually that there are also superconducting correlation even in the second band. And if you see here, the superconducting transition temperatures is suppressed when you go into the second band. And also with the theory support, actually, there is a model now that suggests that there is actually an additional interband superconducting pairing with the repulsive coupling between two bands. So that would explain the suppression of the superconducting transition. So this situation may not be so simple. Now, what about the transport properties measurements? Well, so there have been few experiments on nanowires and Josephson junctions in the system, or kind of Josephson junctions. For example, ones created by the top gating, local top gating, or in dime bridges. Or this is our early experiments on homogeneous or uniform superconducting nanowires and nanorings. And what is remarkable in all these experiments, people have observed a suppression of the critical current in zero magnetic field, or an enhancement of the critical current, but a very small magnetic field in a perpendicular direction. And this raised a lot of discussions about possible p-wave pairing in the system. So there was advocated in some of the works. Well, we had some other model that I will bring to your attention later on. So this was basically the motivation for our work. So there are some indications of unconventional pairing. So we would like to see it more into detail. So our aim was to make a reproducible systematic measurements of these effects in transport in nanowires, maybe weak links, and see if we can get some clear picture about what's going on here, and if we can get establish some model of the system, right? So just a few words about the sample fabrication, because it's very important here in the context of the work. So we use a special technique that we developed already some time ago by my former PhD student. Here these references. So it uses the argon ion implantation for patterning of the system, and it's a very interesting thing for two reasons. So it appears that if you just shine low energy argon ions on this sample, it becomes insulating, and we have realized that this is just because of the ion implantation. So if you use, like, for example, e-beam lithography, you create a structure product that exists, you can irradiate with the ions, you can make everything insulating, but the protected area will remain metallic. So you can pattern very nicely this way. So the two big advantages of this technique is that actually doesn't require the physical removal of the film. So the film is still perfectly remains, so it leaves the planar structure. And actually, it's just the by-side information, but you can actually make a reversal process. You can annihilate, you can remove the argon ions. The system restores to the perfectly initial state. So you can erase your structure, and then you can create a new one on the top of it. But for this work, another important feature of this technique is relevant. Actually, when you radiate, you do not immediately make it insulating, but you can control the metal to insulator transition gradually. So by controlling the dose of the ions, you can tune the system, the resistivity of the system from the metallic into the insulated state. You can very well control it away. So what we did here in this work is we created the channels from a few hundred nanometers to 1 micrometer wide. And then using this technique, when we made everything insulating around, and then we have created, we irradiated a very, very narrow strip line across the channel. So it's like a break in a channel where we did not make it completely insulating, but we just suppressed the metallicity in this channel, just in the hope that we can make such a big link in the system. And the width of this line in the best case was 50 nanometers. So with the coherent length of the system between 35 to 50 nanometers, we hope that there will be some big link behavior. Okay, so what do we see in the transport then? Well, to our big surprise, we did not see any qualitative difference between the devices that had uniform structure and the devices with these big links that we have artificially created across. And you see the critical current of both systems is very similar, and the qualitatively they look very much the same. Now, the only big difference is if you look at the gate voltage. And so the critical current, both the critical current and the normal resistance of the device with the artificial big link is suppressed much, much faster as compared to the uniform device. So how do we understand that? Well, apparently we have to admit that the system is intrinsically inhomogeneous, and it's not we who discovered that. In few words before us, for example, looking at the broadening of the superconducting transition or measurement of the superconductor stiffness. So essentially, the model that proposed that the system has intrinsic filamentary structure consisting of the superconducting puddles that weakly connected between each other. Of course, it depends on the place where you are in the phase diagram, depending on the gate voltage, but essentially across the whole phase diagram, you would expect this kind of behavior. So it means that when you create an additional weak link, it doesn't change the property of the system very much because plenty of the weak links are already there. It only helps us to control the transport in this particular place and a little bit way with the gate voltage, right? So for the rest of the talk, I will focus on both devices, but remember that the behavior is actually controlled by the intrinsic properties of the system. Now, the central result of the work was when we looked at the magnetic field dependence in the perpendicular direction. So you see what we observe here is a very, actually huge effect of the enhancement of the critical current when we apply a relatively small magnetic field. So the effect is much bigger that was been seen in the previous experiments, and I will explain later why is that. But also look here, we see that, well, you can clearly see it just as evolution of the AVI characteristics here. And I note also here that the retracement current does not depend on the magnetic field at all. But also there is an asymmetry of this pattern relative to the sign of the magnetic field. And I should say this is extremely robust and reproducible effect. It doesn't depend on the cooling history. It doesn't depend on if you apply the magnetic field. During the cooling superconducting transition, we see it on all devices, and we believe that this is kind of an intrinsic feature of the system rather than depending on the local flux, trapping, or some other effects. So a little bit more experimental data on that. So we see the effect on the perpendicular field. When we apply the parallel field, there is no effect at all. So just not changing the critical current. And again, we see it both in the devices with the weak links and without the weak links. So why do we see this effect so strong in our case? So apparently they have realized that the effect is very sensitive to the dimension of the device. So when we all experiments are focused on really nano devices like 100 nanometer nanowires. So in this case, we just randomly made wider devices, we have realized that in wider devices, about 1 micrometer, the effect is greatly enhanced. If you go to even wider devices, about a few tenths of micrometer, actually the effect disappears. We don't have a systematic study on that. It's still a very interesting effect, but I will come back to this. Yeah? So, but this is, we believe this is the reason why we see. And you see, you may argue that there is some kind of, because of dimension, if it's interference effect, it may depend on the size of the device, so you have to go to very high magnetic fields. I don't show it here, but we went to high magnetic fields, like 100 millitesla, and we don't see any single effects in the small devices. Okay, so finally, the last piece of the experimental results is when we look at the gate voltage dependence, which is also very peculiar. We see that the applied gate voltage suppresses the critical current, but also suppresses the effect of the enhancement of the critical current. And actually, this effect is suppressed well before you suppress the superconductivity, which is very peculiar. And then at the same time, you'll be very careful if you look at this effect, the asymmetry of the two positive and negative branch on the magnetic field actually changes the sign at low gate voltages. So if you plot the difference of the critical current between the positive and negative magnetic field, you will see that it crosses the zero and the low gate voltages are actually least. So very peculiar and very strange behavior. So we thought many possible scenarios. So let me just try to go through some classical mechanisms that we try to understand this effect, because it's not very often observed, and I would say this is an unconventional effect in superconducting devices. So, well, the first effect that I can recall is back in the history. Is related to the effect of the rendered superconductivity, or Yakarina-Petrov effect, which is essentially the effect of the compensation of nocturnal exchange fields in the material by the high magnetic field. Well, we can definitely rule this out because of two reasons. Well, the fields that you need for that is very, very high. They're much higher than we have in our experiments, that will suppress all superconductivity in our samples, definitely. Also, it should be absorbed both in the parallel and perpendicular magnetic fields. And the critical temperature in this case also should be sensitive to magnetic field that we do not observe in our experiments. Then there was another very interesting mechanism that we actually advocated in our original paper, the first paper where we observed this weak enhancement of critical current. It is actually related to the suppression of the spin flip scattering on the magnetic impurities by big magnetic fields. And it has been seen in only very few experiments previously in history in, for example, molybdenum, germanium, and aluminum gold nanovites. The effect has very similar features that we see in our experiments. However, it is actually supposed to be enhanced in the parallel magnetic fields, because essentially it's a trade-off between the effect of the suppression of the exchange scattering and orbital depairing mechanism. So when you apply the parallel magnetic field, the effect is supposed to be enhanced. But we see no effect in the parallel magnetic field, so I think this was kind of a smoking gun experiment to rule out this possibility, even though it is a very interesting mechanism to propose. So then finally, this mechanism came out in a discussion with Sophie Guéron. This is on the right, the paper here. She was very much convinced that what we see here is actually due to the non-equilibrium effects. But, well, essentially, we are talking here about the effect of the quasi-particle poisoning from the normal electrodes. Now, we don't have any normal electrodes, but if we believe that our system is inhomogeneous and we have some kind of normal puddles in our system close by, then we can think about some kind of quasi-particle injection. When you apply the magnetic field, you weaken the superconducting gap and you would enhance the thermalization of the hot quasi-particles, and by this you can actually increase a little bit the critical current of the system. This has been seen in other systems also, like in zinc nanowires, and this is the work by Sophie Guéron, in tungsten proximity nanowires with the silver. Well, the strong argument against this, there are two strong arguments against this. So first argument is that the thermalization effects would be much more pronounced in the narrow, small volume devices. And we see opposite trend, that we see that in the smaller devices, this effect almost disappears. And another thing is that in this scenario, also the retractant current would be very sensitive to the magnetic field, because it's essentially a thermalization mechanism. And if you change the thermalization, the retractant current will also be sensitive to that. But we see no effect of so. That brings us to another possibility, another scenario, which basically you can already say from the very beginning that see effect only in perpendicular magnetic field, you probably have to deal with interference effects, right? And well, then there'll be a few experiments when people have seen a very similar magnetic field dependence of the critical current in a system with the proximity of the conventional superconductor with the topological insulator materials. And essentially what happens there is a formation of the chiral POS wave order parameter channels in the proximity region. And that results in interference of two channels, giving you the minimum of the critical current as a function of the magnetic field. So basically, in a similar way, what has been seen in SFS Josephson junctions, right? So, well, this is very similar to our work qualitatively, but of course we have no microscopic model to claim that we have such a scenario. So, and moreover, if you think about this traditional way of treating this approach of the Josephson junction with unconventional order parameter, so you have two channels where you have 0 and pi phase shifts. It would give you nicely the minimum of the critical current, but it will never give you an asymmetry of the lobes, the positive and negative magnetic field. So then we had a lot of thoughts and discussion with Claudio and Mario and Roberta, and they came out with a suggestion that why don't we introduce a third channel? I mean, this of course a complicated model, but the idea was that we have no microscopic reason to believe it's just one channel but many channels, but let's try to develop the simplest model we can that would qualitatively explain the results. So basically what they have done, they have added a third channel to the consideration and just a channel with a second harmonic. That may be very well due to some interband pairing between the different bands in the system, or maybe to the other reasons. I don't know this for sure, but this is just oversimplified proposal. Then what you do, you can just calculate the total critical current of this system and calculate the maximum critical current, supercurrent, and calculate the maximum critical current by maximizing supercurrent as a function of the superconducting phase. So what do we obtain then? Well, now we have a lot of parameters here. We have the width of the channels, we have the relative strength of the critical currents of different channels, but it appeared to us very surprisingly that actually in the very, very wide phase diagram of this system, if you take all these parameters arbitrarily, it qualitatively very well reproduces the effect that we see in our experiment. So we see both the minimum of the critical current, and we see the asymmetry, and moreover, now if you look on the right plots here, so this is a bit more complicated, but essentially this R value tells you about the amplitude, so difference between the two peaks in the positive negative magnetic field, and this tells you the data as it tells you about the sign. Yeah. And what we found is that if you go to peculiar places on this phase diagram as a function of the strength of the relative strength of the channels, you can actually find out clearly that there is also a change in the symmetry. For example, if you introduce the strong critical current in the third channel, then current in the third channel, you see that there is regions where you can actually reproduce what we see in our experiment, also with change in symmetry. And you may link this observation to what we see in our gate voltage experiment. So you can think that we can tune the relative strength of the channels by the back gate voltage, and thus you follow this phase diagram, right? So again, this model doesn't have any microscopic ground, so we still have to establish that. But we're very happy to see that we can get this very good qualitative agreement between this model and the experiment. So this basically brings me to the summary of my work. So I have shown you that we see a very giant effect of the enhancement of the critical current, which is very anomalous in the small perpendicular magnetic fields in the nanostructures of this oxide interface. And we came out with a model that proposes the existence of the three channels with the intrinsic phase shifts that qualitatively agrees with experimental observation. So basically, we hope that this is a clear indication of the fact that we do have an unconventional superconducting variant of the system. But of course, we have to make phase-sensitive experiments and probe the current phase relationship in the system. And we are trying to do now the microwave measurements, but it's very tricky because it's a strontium titanate substrate, so it's a lot of losses and it's not a very easy experiment, but that's still an ongoing plan. So with this, I would like to thank you for your attention and be happy to answer any questions.
Now the session is open for discussion. Have a question here.
Thank you for the very interesting talk. You mentioned that you do not find any dependence on the critical temperature on it.
No.
But in this material, I'm not an expert, but I think with the gate voltage, generally the critical temperature changes, no? Even without all this effect. Like just the layer itself, because of modulation of the density, carrier density.
So what is your question about gate voltage?
My question is that I'm not an expert on material, but I seem to remember papers where they observe by modulating the carrier density.
Yeah, that's a huge effect. Yeah, you can tune the whole system from the superconductor into
right. So you're not in that regime.
No. We are still always in. They actually always in close to optimally doped, slightly under doped still. So we are well deep in the superconductor region.
Okay.
Yeah.
Thank you.
So this is the data from.
More questions, comments? Thank you very much.
Thank you. So let's move on to the next talk. I assume because this depends on the weight of your.
Right.
I assume that penetration depth is huge, right? So there is no magnetically homogeneity on this side.
No, we think it's completely. No. This we thought a lot about this. So our first idea was based on exactly this, that we have some current, inhomogeneity distributions that would definitely give you this symmetry break-in effect. But I mean, again, the thing is that it's all independent on the geometries. I mean, we prove different geometries, different bits, different structures, and they all show exactly the same effect. It was extremely remarkable, actually. Yeah, so we couldn't figure out if there's any correlation between the shapes, between the dimensions. The only thing that when you go to very small sizes, then the effect becomes very, very big. And our actual interpretation of that is that in all these experiments previously that treated the system as inhomogeneous, these puddles with big leads, they think that the characteristic size of this inhomogeneity is on the order of the 100 nanometer. So we actually, when we go to the small regime, we get into the situation when we become comparable to these inhomogeneities, and then things become completely different. Yeah, you don't have any more the macroscopic current flow.
Maybe I understand it, but in your model where you have 3 channels, you still have a pi junction, right?
Right. So this is an important ingredient. Yes, exactly. So so the only two that we say the model is essentially this. It's a very simple model. We say we do have two kind of order parameters. So we have the positive and negative sign in 2 different bands, but this is not sufficient to explain the result. So we have to introduce the second or the third channel that's actually intermixing of them. Yeah, that would give you the second harmony.
Thank you.
Okay, and the last question here. At least in the normal state of RC, it has been shown that the system can be very inhomogeneous because of the formation of green walls in that system. How much is known about in the superconductor state? Could this be the origin of the?
I intentionally didn't go into this discussion in my talk because it throw us to very, very long discussion. So briefly, we actually tried to make these experiments deliberately together with Bina Kaliski when we tried to make very low nanowires and tried to see placing on them and having this domain balls and this strontium titanate would somehow affect. Well, we do know that they do affect because when we go into the depleted regime, when we apply the negative gate voltage, then what happens is that sometimes the device the resistivity of the device just goes like infinite, it just becomes insulating. But when you warm it up above this magic 105 Kelvin temperature and cool it down again, everything is back to normal. Yeah. Now, so there's definitely an effect on the super. We don't know if these domains actually contribute to this effect. This is a very interesting question, but It is very hard to answer because we don't have any image, especially when we're talking about, when you speak about the microscopic objects, that's fine. But when you speak about a nanowires, there's also a clear picture that the presence of the nanowire itself can affect the domain structure. So it's a very intricate question, but indeed it's one of the things we are collaborating with, and we have now a very interesting experiments actually that we're going to publish on anomalous Hall effects in the systems and nanowires in this normal state that show actually when you drive the current into the system, the Hall effect becomes nonlinear. So that's clearly related to these effects of the domain rules.
Thank you very much. This time, Alexei again. And the third talk of this session is by Roland Villa from the Institute of Technology, who will present the homogeneous strain causes time reversal symmetry breaking in strontium rectangular oxide. The floor is yours.
Can you hear me? So thank you very much. I would like, first of all, to thank the organizers, Herman, and all the organization team for giving me the opportunity to present here our recent work. I think we will be talking about strontium ruthenate, so this is a bulk 3D material. I still think it fits quite well into this session about low-dimensional superconductivity, because as you will see along the talk, we will be discussing about what happens close to dislocations, which are quite filamentary objects in a 3D matrix. So this is the outline of the talk. So we have to discuss first why is strontium ruthenate still so puzzling. So the material is around for quite a long time. It's known to be superconducting for almost 30 years, and still we don't quite understand the material. There's quite some open questions. And then we will discuss the view of inhomogeneity in the material and how this can help us to understand what's going on in this material. This material has been done in collaboration with Matthias Hecker, who was a doctoral student in Karlsruhe and who has now left for Minneapolis to work with Rafael Fernandez, and also Jörg Schmalian was part of this collaboration. And the publication is indicated here. So let's first of all review a few experimental signatures of the material. So the strontium ruthenate is a layered material very similar to the cuprates. It is a material that by now can be fabricated with an extreme electronic purity. Here we see a laser ARPES experiments that show that it's a multi-band system. It's electronically anisotropic, so it's because it's a layered material, it's almost two-dimensional electronic system, but it can be fabricated with in a quite clean fashion. It develops superconductivity below roughly 1.5 Kelvin, as can be seen here in a transport experiment. And then quite some time ago, it has been shown by polar Kerr measurements that there is time reversal symmetry breaking going on in this material, and the signal for time reversal symmetry breaking appears at the same temperature as the onset of superconductivity. And then there's also ultrasound attenuation measurements that show that this material is a nodal superconductor, which is another experimental signature of this material. Now, quite recently, in the last 3-4 years, there have been quite new developments in this material. First of all, there have been experiments of an NMR night shift, which has been revisited after quite old night shift experiments. And these new experiments show that there is a very clear spin relaxation at the onset of superconductivity, which means that we are in the presence of a spin singlet pair. In contrast to earlier beliefs where this spin relaxation was not observed, and then one has associated this with more like a triplet mechanism. Also, strain experiments have allowed to study what happens with the superconducting and time reversal symmetry breaking transition under strain. And we see here that there is a splitting of these two transitions. So on the one side, superconductivity gets enhanced under uniaxial strain, and the time reversal symmetry breaking transition is roughly strain independent for moderate strain fields. which points to a multi-component superconducting state. And then there is a third quite important signature, also in the context of this talk, which is what happens to these two transitions in calorimetric experiments. So we see here the specific heat data of the superconducting transition for different strain values. We see again from left to right that the Tc increases under strain, but at the temperature, which is roughly 1.5 Kelvin, where time reversal symmetry breaking is observed, there's absolutely no signature in the specific heat data. And this is, of course, a bit puzzling, because usually if there is a second superconducting order parameter that develops, there should be a quite strong signature also in the specific heat data. So we are looking for a multi-component nodal spin singlet superconducting pairing state, and we have to understand why time reversal symmetry is broken without a specific heat anomaly. And what we can do is we can go and study the point group table of this material within a D4H point group. We have different irreducible representations which tell us what are the superconducting states looking like. We have an S wave, G wave, different one-dimensional D wave components, and then we have an EG channel which has a two-component irreducible representation. And we can try to understand which are the possibilities to explain the material. So one possibility is to say, okay, let's take the lowest line here, which is an EG channel where we have two degenerate superconducting order parameters. Then, okay, something did not show up here in the PDF conversion, I'm sorry. The problem with the appearance of a two-dimensional order parameter is that as soon as we apply strain, we would move the two superconducting transitions apart, but the specific heat anomaly associated with the second transition would be of the same height as the first one, which is in clear contradiction with what experiments point to. The second option would be to just take two single component superconducting order parameters and then consider the situation where these two order parameters roughly appear at the same temperature. Yeah, we know that without strain, there is time reversal symmetry breaking and superconductivity appearing at the same temperature. So we have to argue why two symmetry distinct order parameters appear at the same temperature, and then we have a bit of trouble arguing why there is such an accidental degeneracy, because there is nothing that forces us to have two symmetry distinct order parameters to appear at the same temperature. Okay, so what we propose instead is to have a different view, and this view is more related to inhomogeneities. So we consider that strontium luthenate is a D-wave superconductor if it's perfectly clean, and that it respects time reversal symmetry. So it's most likely a dx squared minus y squared superconductor. And then what makes the entire physics interesting is that time reversal symmetry occurs because we have dislocations in the crystal, and along these dislocations there is a subleading pairing gap, likely with G-wave symmetry, that can nucleate and that can cause the breaking of time reversal symmetry. And the reason why I say likely G-wave symmetry will become clear in a moment. So why do we think that strain is important in this material? So here are a few experimental signatures, again, justifying our choice. On the one hand, we know that the electrical response is very dependent on the sample quality. So if we have different samples and measure the transport properties, then we see that the transport properties can vary quite strongly depending on the sample quality. Also, TEM images show that there are quite clear dislocations in the material. There have been squid measurements that showed how the local transition temperatures change as a function of the position on the sample. And also there we see that there is quite strong dependencies on where the magnetometry is performed. And then also from ultrasound, resonant ultrasound experiments, there is an indication that at the superconducting transition, there is a jump in the C66 elastic constant, which is associated with the B2G channel. And this is the reason why I believe that a D wave and a G wave component are a good pairing, because a D wave and a G wave component would together couple to such a B2G mode. So now let's go a bit more into the technical details. What we do is we write down a Ginzburg-Landau free energy for a two-component order parameter. No, I'm really sorry that some, I don't know. Yeah, that's a bit unfortunate because half of the slide is missing. All right, so let me try to explain what we can see. So we have a Ginzburg-Landau free energy for a two-component superconducting order parameter. So these psi's are two components, which are our D wave and our G wave superconducting state. And this would be for a homogeneous situation. We would just have a quadratic term and different quartic terms. In addition to that, we will have to include gradient terms because we are interested in an inhomogeneous situation where we have a dislocation. And I'm wondering whether I should somehow switch because it's probably going to be difficult if I can show the formulas. I think this is a PDF. Oh, this is PDF. Yes. May I quickly switch to have, yes? Can I? I'm sorry. Yeah, thank you for your patience. Sorry for the inconvenience. So, yes, so we start from a two-component superconducting order parameter because we want to nucleate a G-wave component due to strain. So what we have here is we have a first transition where we go into a D-wave superconducting state. But as I said, the subleading component has to be somewhere there. So there will be a second G-wave component that would appear at a much lower temperature. Now, in order to have time reversal symmetry breaking, what we are actually looking for is for a relative phase between the D-wave and the G-wave component that requires a non-trivial value, which means a value different from 0 or pi. Okay. We add gradient terms, this I've already mentioned before, and then we add a dislocation and a coupling to the dislocation. Now, a dislocation in general will introduce strain fields into the material, and these strain fields, again, we can decompose them into different symmetry channels, and therefore there are different ways that strain can couple to our multi-component superconducting order parameter. And there can be either a local symmetric change of the local TCs, around the dislocation. We can have an increase or a decrease of the transition temperature. And another coupling can change the relative TCs locally. But there is also the possibility of having a direct admixture between the D wave and the G wave component. And for this, we need one very particular strain component, which in this case is a B2G strain. Okay, so what we are looking for is what happens near such a dislocation in the presence of a D-wave superconducting state. Yeah, and then we take a very simple form of a strain field around such a dislocation. And what we notice is that on one side of the dislocation, there will be a tensile strain. On the other side of the dislocation, there will be a compressive strain, which means that this object here has a positive sign on one side of the dislocation and a negative sign on the other side of the dislocation. As a consequence of that, if we look far away from the dislocation, this direct coupling will immediately induce the subleading superconducting state, which means that to the left of the dislocation, we will produce a D plus a tiny part of G component, whereas on the right of the dislocation, we'll have a D minus a tiny component of the G-wave superconducting order parameter. Now, there are two ways to connect these two regions. We can either go from D plus G to D minus G by suppressing the G component order parameter and bringing it up to the other side with the opposite sign. And that's the generic way one would go from plus to minus. But there is another way one can go from plus to minus, is by winding the order parameter in the complex plane and bringing it from plus, which is phase phi, to minus, which is a phase pi, through the complex plane. And because the sign change that we have here needs to cost some gradient energy, it is a balance of gradient energy versus winding in a complex phase, which will determine which of the two options will be favored. And then we can study this problem analytically and find analytic expressions for what is the temperature at which the system prefers to wind the phase rather than going from plus to minus via sign change. And this phase winding will locally around the dislocation break time reversal symmetry. Okay, we can complement this by numerical simulations. And then what we do is we decompose, we have a plane, we have the dislocation pointing out of the plane, and then we have here four regions showing the real and imaginary part of the D wave, the real and imaginary part of the G wave component. And we see that if we are at high temperatures where the D wave component has developed, there is, due to the dislocation, a D plus G and a D minus G, as we anticipated. But in the imaginary parts, nothing is there. And if we go to a temperature below that symmetry, time reversal symmetry breaking temperature, the dislocation will nucleate an imaginary part of the G wave component, which then tells us that the phase is winding rather than changing sign as we move across the dislocation. And the numerics agree very well with the analytic results that we have derived. Now, there is one more problem, namely that the free energy that I wrote in the beginning is invariant under such a transformation where we send the order parameter of the D wave to itself and the G wave to its complex conjugate. And what this invariance means is that if we want to wind the phase from plus to minus, we have actually two options. We can either wind it to the upper or the lower complex plane. And these two options are like a spin degree of freedom that is an Ising variable, and that tells us that we are not yet fully done, because as we look along one dislocation line, maybe at this point the system wants to wind the phase along one direction, but at another position of the dislocation, the phase winding will be in the other direction, which means that along one single dislocation, the winding doesn't necessarily need to be along the same direction all the time. And then this maps our problem of the dislocation to a one-dimensional Ising chain. Now, one-dimensional Ising chains are known not to order at any temperature, because kings and anti-kings will always destroy a long-range order. However, what helps us here is that a one-dimensional Ising chain is at its lower critical dimension. What it means is that as soon as we have a very weak coupling between dislocations, and this coupling can be exponentially weak, then this will be an anisotropic two-dimensional system instead of a one-dimensional Ising chain. And this indeed has a true phase transition, which is then only the true temperature at which the global time reversal symmetry will be broken. So we have denoted by this time reversal symmetry breaking star the temperature at which locally on one plane phase winding is favored, but the true bulk phase transition where time reversal symmetry breaking occurs is only once all the dislocations decide for which of the two spin degrees of freedom or windings they want to order. But this coupling, even if this coupling is small, the true time reversal symmetry breaking transition is quite close to the one with T star. Now there is a question related to the specific heat. What we did is we looked at the specific heat for one-dimensional Ising chain, for an anisotropic two-dimensional Ising chain, and then in order to estimate the signature that we anticipate for such a time reversal symmetry breaking transition, we compute how much weight is shifted into that peak of the phase transition, and we compare it to the electronic specific heat associated with the superconducting transition, and we find that it is small with numerous small parameters, which then gives us a very good understanding of why such a time reversal symmetry breaking transition will not be visible in specific heat measurements. Okay. So let me briefly touch about future directions. One thing is to envision how one can use this dislocation engineering to induce a time reversal symmetry breaking in such materials. Another idea is to train the time reversal symmetry breaking order parameter by a mixture of strain, which is naturally present in the material, and magnetic fields. And then also to look for spontaneous currents or magnetism that develop around these dislocations. And for this, we are currently looking at how the local density of states near these dislocations look like, and what current patterns we expect for this system. Okay, one thing that we still don't quite understand is why does the time reversal symmetry breaking transition coincide at zero strain so closely to the superconducting transition? And this is also another open questions that needs to be addressed. Okay, finally, I summarize by repeating that we believe that strontium ruthenite is first and foremost a D-wave superconductor, and that all the exotic part, which is related to time reversal symmetry breaking and to the multi-component nature, comes about because we have strain inhomogeneities in the material. And because of that, the time reversal symmetry breaking transition has only a very tiny specific heat anomaly. And with this, I'd like to thank you for your attention, and I apologize again for the interruption we had. Thank you very much.
We have time only for one question, please. Yeah. There were just some jumps on school interference data which favor strongly px plus ipy, and would be rather difficult to reconcile with any given area. So can you comment how the picture, you just ignore this piece of data, or you can also
I cannot very precisely comment on that. I would have to look at that experiment. Thank you.
That's one. Yeah, well, maybe I would like to comment on that. So, I mean, more than 10 years ago, we measured the superconducting gap of this material, and we found a result which is completely compatible with specific heat, and which is also completely compatible with SOX. Now, it still may be something more complex, but I mean, for 20 years, we have been thinking that this material is a superconductor. And because of the night shift. And now the night shift measurement turns out to be not right. So, okay, so we have remeasured that again, and this is it. So I think that you come to the point. So if there is something interesting, this material, it is located at defects and the positions where there is some inhomogeneity or something strange. But I think that all the story about triplet superconductivity is hardly to be sustained. This is one.
Okay.
Thank you very much.
Thank you.
Now we have the last talk of this session. Unfortunately, Jos Wilhelmos could not present today, so it will be online, and it's by Vladimir Konin from Moldova State University. He will talk on topological transitions in AC/DC driven open superconductor.
Good afternoon, buenas tardes. Can you hear me?
Yes.
First of all, I would like to thank the chair and the organizers for the possibility to represent here our recent research results on open superconductor nanotubes. This work was performed together with Alexander Dobrovolsky. Main part was done at our Institute for Integrative Nanosciences at Leibniz Institute for Solid State and Materials Research in Dresden, with involvement of State University of Moldova and University of Vienna. Here is an outline which gives you the idea of the structure of this work after a short introduction of the advanced superconductor nanoarchitectures. I will tell you the effects which have been found recently within numerical simulations, including dynamics of topological defects in the low frequency regime, effect of magnetic field on the dynamics of topological defects, effect of the current modulation depths, effect of the AC frequency, and of the DC magnitude on the superconducting transition in such systems. When we're speaking about quantum materials at nanoscale, this is the title of our workshop. One of the avenues in these studies is related to superconductor nanoarchitectures. And I would like to recall you that superconductor three-dimensional nanoarchitectures feature magnetic field inhomogeneity, non-trivial topology of superconducting screening currents, and complex dynamics of topological defects. Recently, the results in these fields were represented in my book on self-rolled micro and nano architectures, including both superconducting and non-superconducting 3D nano architectures, and also in a very recent perspective article of Applied Physics Letters, together with Alexander Dobrovolsky, which is referred to here. New possibilities for experimental investigation and application of superconductivity have been revealed in samples with curved geometries. And here I would like to recall that superconducting 3D nanoarchitectures have been successfully fabricated by a few methods. One of them is rolling up, as indicated here in the second panel, which show multi-wall superlattice and helix made of rolling up of niobium, and also by direct writing of 3D nanoarchitectures, for example, made by focused electron beam induced deposition. Is the third panel as fabricated in Frankfurt and Vienna, and also focused ion beam induced deposition. This last panel with nano helices, which were fabricated and studied in Zaragoza and Valencia. Of our previous studies, I would like to attract your attention to this scheme of the generic system, which will be important in order to report the new results. Imagine that you have an open nanotube as shown here. If you roll up a membrane into a tube, you do not receive a full nanotube, you receive an open nanotube. And then it's possible to attach contacts to two banks of this opening, which we will call slit. And if a transport current is put through one electrode to another electrode, the shape of the current lines is like Greek omega letters. If this open nanotube is put into a magnetic field orthogonal to its axis, the pattern and the dynamics of order parameter is very strongly dependent on the magnetic field and on the transport current. Close to critical current, lower but already significant transport current, we observed in the numerical simulation this topological transition, which is shown in the first panel, and with increasing magnetic field, we observe a change of the pattern of superconducting order parameter from vortex chains to more dense vortex chains or double chains via an intermediate regime, which is represented in panels 3 and 4. The magnitude of the order parameter is suppressed, but the analysis of the phase shows that there are multiple events of nucleation of vortex anti-vortex pairs which move under the Magnus force, and this motion is very fast. It's 3 orders of magnitude faster than motion of vortices in regular chains. Due to this fast motion, the induced voltage is rather high, and this gives rise to a peak in the induced voltage, as shown in the first panel. What is behind this peak? Behind this peak, there is a topological transition from a situation with only 2 superconducting screening currents in both halves of the tube to this configuration with 4 loops of screening superconducting currents, which is shown in the central panel, and the locus of vortices and anti-vortices is just in between the 2 new loops of screening currents, which are occurring only when this nanotube is in relatively strong transport current. So this is a scheme which was reported in 2020, and we put the following question: what will happen with this evolution when we will modulate the transport current as shown here in the picture? In the central red frame, you see that the transport current density is modulated with a certain frequency f, which will be essential parameter of our investigation. Our approach is based on time-dependent Ginzburg-Landau equation in association with Poisson equation for the scalar potential, and the boundary conditions for this scalar potential involve the transport current. An important feature of this system remains a strong spatial inhomogeneity of the normal magnetic field, normal to the surface, because as shown in this panel, magnetic field is orthogonal to the axis, and therefore its normal component is modulated according to the sine law. This problem has many parameters, and I will start giving you the obtained results with a case of a relatively low frequency regime at a relatively weak magnetic field. So here we have a kind of set of snapshots starting from time 1 to time 8, and these time points are all indicated in the central panel. They give an idea of what happens with superconducting order parameter distribution when the transport current experiences one period. The panel number 1 gives a distribution of the order parameter with maybe a few vortices which move. The motion of vortices is shown with arrows, but the induced dissipation is very weak. The voltage is here in the central panel close to 0. When we increase the current with further evolution, two phase slip lines develop close to the banks of the slit, but at some distance. This already gives rise to more dissipation, and therefore the voltage induced by these phase slip lines is a little bit larger. When we go further to point 3, this phase slip lines becomes broader, and there occur also some phase slip precursors even in the region opposite to the slit, as shown in panel number 3. And at stage number 4, we arrive at the maximal induced voltage, because the phase slip regions are maximally developed here. And in this case, we have a significant region of normal phase just opposite to the slit. This is the maximum of the induced voltage. When we further increase the time, the current further decreases, and in the central part of this panel 5, we see something which is absolutely unknown and non-typical for planar membranes. They are developed some azimuthal phase slips which tend to join both halves of this tube. We will speak about them later on. At further increase of time, we still have some phase slip lines as shown here, and at stage number 7, phase slip lines start to split into vortex chains, and this is linked to decrease of the induced voltage, because we are in the state which is mainly superconducting. The last panel 8 shows again a state with dominant superconductivity, except maybe some vortices which return us to the initial position. Such a evolution of the order parameter is typical for all pictures which will be represented later on, but I will not go into these details, so please keep this typical dependence on time in mind. What is the effect of the magnetic field? If the magnetic field is absent, this is an upper panel 1, then 2, and 3. Then the vortices which might occur at the initial time, they do not have a preferential direction, and therefore the induced voltage is 0. By the way, the fact that the occurrence of vortices is facilitated just opposite to the slit in the central part of this tube is similar to the symmetry driven occurrence of phase slips in planar membrane. But then we have distinct differences. When we go now to larger time, panel number 2, we observe an occurrence of phase slips close to both banks of the slit, but also a phase slip joint between both halves. And this and similar effects, which are also in panel 3 and in subsequent slides, which I will show, they indicate that this kind of topological defects which develop in open nanotubes under combined DC plus AC current, they are holistic. They belong to the whole system rather than to half tubes separately. In case 3, we have just the maximum of induced voltage because superconductivity is significantly suppressed. Now let's go to a higher magnetic field, even higher than we considered at the previous slide. It's here 10 millitesla. At the very beginning, we have a combination of a phase slip line opposite to the slit, like it was in the case of DC current, which I started with, but also some chains of vortices which move in the parts of this tube where the magnetic field is practically normal to the surface. When we go to a higher current with running time, we see that this central phase slip line practically dissolves, but the former vortex chains give rise to two well-expressed phase slip regions, which broaden and give rise at panel number 6 to the maximal value of the induced voltage, the highest dissipation. The next slide is intended to represent the effect of the current modulation depth. This is a ratio of the magnitude of the modulated to DC current density. And here the very first line gives you the value of this current modulation depth. The first series of panels are related to the maxima of the induced voltage, and the lowest series are related to the minima of the induced voltage. If the current modulation depth is relatively low, we see a transition from one phase slip, from one phase slip line opposite to the slit to two regions of phase slips which are broadened, and this is similar to what we have seen in the previous slide. But when the modulation depth of the current increases, we see, first of all, very complicated patterns of phase slips. In the panels on this slide, all phase slips are encircled with some dashed contours. And you see that the phase slips at increasing value of the modulation depth, they form some shapes which also extend to the azimuthal direction. very typical example is panel number 7, where you see how a phase slip turns from azimuthal to paraxial direction. At relatively deep modulation, we have practically superconducting state at minimum, with maybe a few vortices moving, but at maximum we have a very well developed phase slips which give the main rise, the reason for maximal induced voltage, as shown in the central panel. Okay, I would like still to attract your attention to 2 other dependencies, and this is one of the key results. It's effect of the AC frequency on the dynamics of topological defects. And here we start with a relatively low frequency modulation. You see the number 3 gigahertz. In this case, we give only the maximum of the voltage. These are distribution of the amplitude and phase of the order parameter. As you can see from panel 1, at maximum we have well-developed phase slip regions, and the fact that they are really topological defects is supported by the analysis of the phase portrait. I would like to recall that this is a snapshot. This picture changes with very high frequency. The typical pattern of voltage is represented in panel 7. It's modulated with the frequency 3 gigahertz signal, and the fast Fourier transform of this signal shows nice sequence of first, second, third harmonics with dominance of the first harmonic. So this is a case where the voltage is very effectively induced. If we increase the frequency to 6 gigahertz, we observe this very special pattern of the time dependence of the induced voltage, which is shown in the central panel 8. It represents intermittency between relatively low values of induced voltage, on average 1 millivolt, to relatively high values of the induced voltage, approximately 3 millivolts. And the typical time of this intermittent behavior is here about 10 nanoseconds. So this is a combination of high frequency modulated motion with low frequency intermittency. Therefore, the fast Fourier transform, which is shown in panel number 11, reveals not only a first, second, third harmonic, but also a rich spectrum at low frequencies. And in the inset, I hope you can see it, there are 2 peaks which are dominant in this pattern, and they are at 0.1 and 0.25 gigahertz. This is significantly lower than the induced voltage, and therefore it is not an effect of the induced voltage. we relate it to the internal dynamics of the superconducting order parameter, and the distributions of the order parameter in panels 2 and 5 show that at maximum, this is a situation with well suppressed superconducting order parameter, therefore the voltage is so high. But if I would have shown minimum, then there would be almost everywhere this red and yellow color, which indicates high level of superconducting order parameter and correspondingly relatively low induced voltage. But if we increase the frequency still higher till 10 gigahertz, we arrive at a pattern which is shown in panel number 9. It's again mainly harmonic with dominating first harmonic, also expressed second, third harmonic, but with no significant contributions to the low frequency field. And what is this stage? This stage is mainly superconducting. As you see here, the picture of the maximum, the major part of the tube is superconducting, and only close to the banks of the slits, there are some vortices moving. These vortices cannot produce high induced voltage, and here the main contribution to this voltage is from a very narrow region near the slits, where a transition from normal current in contact to superconducting current in nanotube occurs. Now I am approaching already the last.
Can you hear me?
Hello?
You have to summarize. We are at the last minute of the talk.
Yeah, no, but I am approaching here the last slide, which I would like to also comment still in more detail. This is the effect of the DC magnitude on the superconducting transition. Here, we change the magnitude of the DC density, and at the value which is taken as the first, I think it's clear that almost all superconductor is in superconducting state. Therefore, the voltage which is induced is low. It's still not zero, because we have this transition between the normal state in contacts and superconducting state in the tube. And from these very narrow regions near the banks of the slit, we still have this induced voltage. But then when we increase the transport current density, we arrive again at an instability. This instability, I would like to emphasize here that this case is already at a high value of the AC frequency, 60 gigahertz. This instability is between the state with significantly suppressed superconductivity, like shown here. It's in the maximum. In the maximum, we have again about 4 millivolts on average induced voltage. And in the minimum, we have dominating superconducting state, similar to the previous case, but there is a regular transition between this two stages during the evolution with typical time which depends on the value of the DC magnitude. When we increase this DC current magnitude, then the regions with decreased or suppressed superconductivity become dominant. What is interesting here in panel 11, we give again the fast Fourier transform. And next to fast and higher harmonics, we have here naturally significant contribution from the low frequency harmonics. And again, two arrows show where are they. And they are remarkably almost at the same place when they were in the previous slide, where the frequency was 10 times lower, and this shows that such phenomena do imply interaction of the superconducting order parameter with relatively low influence of the AC current. Finally, when we still further increase the density of the DC current, we arrive at situation with steadily suppressed superconducting order parameter, as distinct from the previous case. There are already no phase slips. This is simply a uniform normal state, naturally with very high within this set of investigations value of the induced voltage, and no significant components in the fast Fourier transform at the low frequency. So in fact, we observe here a transition from superconducting to normal state, but it's via this intermediate intermittency stage, which is specific for nanotube, and it can be controlled by the parameters of the nanotube. I think here we arrive at conclusions. I would like only to emphasize that the key effect which we observed in our numerical simulations is a transition between two regimes in the superconducting dynamics in such open nanotubes. The first regime is characterized by a pronounced fast harmonic in the fast Fourier transform spectrum of the induced voltage, and it's related either to well pronounced superconducting state or significantly suppressed superconducting state. The second regime is represented by a rich fast Fourier transform spectrum, which joins not only multiple harmonics of the AC frequency, but also low frequency components, which are due to the internal dynamics of superconducting vortices, phase slip regions, and superconducting screening currents. Now I would like to acknowledge our collaborations with Igor Bogush and Roman Rezaev. This work was funded by German Research Foundation, Austrian Science Fund, and I would like to express our thanks to Cost Action for support of this work. And at the end, muchas gracias.
I think we are out of time. It's time for lunch. You have a very short moment for Vladimir. If not, the session will be over. So thank you, Vladimir. It's time for lunch here. We want to thank all the speakers of this live session.
Unfortunately, as we mentioned before, the last speaker could not present today for health reasons, for common reasons. We hope he recover well soon. And yeah, let's thank all the speakers.
Sí, estuve hablando yo ayer con la prima que me llamáis.
¿Puedo escribir en el chat solo para esta sesión?
¿Ah, sí?
Sí, porque a mí no me sale.
A ver.
Mítetelo cuando puedas. Bueno, lo va a ver todo el mundo. Es que yo no entiendo cuándo hacen eso.
A ver. Uy. Ah, no, se
Vale.
habla de eso.
Bueno, esto está.
Sí. Ya está. ¿Quieres? You want to check that it's everything all right? Yeah. Yeah, good, perfect. ¿Quiero? Vale, porfa. Sí, sí. Gracias.
¿Hay que usar puntero o uso el mouse?
Está este puntero, pero lo que prefiera. ¿Quieres comprobarlo? Tranquilo. Porque no empezó la sesión, o sea, vamos a por ahí.
Para aquí todo el mundo. Bueno, ahí está. Perfecto.
Yeah, so well, Welcome to the very last session of this workshop. My name is Diego from Tübingen. I'm chairing the session. And yeah, we start with the first talk. This is given by José Lado on topological and open superconductivity in standardized materials.
Thank you so much for the introduction. First, I'd like to thank the organizer for the wonderful opportunity. It is pretty great to be in this pretty inspiring workshop and be able to do it in person, of course. So today I'm going to tell you about how you can actually create both topological and nodal superconductors using wonderful materials, in particular using dipole materials. And let me first emphasize that all the results I'm going to show you today have been the result of the work of many people that are on today here in this conference. So the idea for today is to focus essentially on the very special class of materials that are called two-dimensional materials or wonder classes. Which are essentially materials that can be isolated in the monolayer. And in these materials, we can find many different types of different orders, going from the semimetals to semiconductors, insulators, from spin-fold insulators, from spin liquids, and of course, superconductors. And among them, in particular, maybe the selenide and the sulfide are one of the paradigmatic dimensional superconductors. And those are the ones that we will be focusing on today. But maybe one of the most important properties of these superconductors is that they can actually be controlled in a way that is completely different from what we can do in three-dimensional materials. In particular, these two-dimensional materials, we can either stack arbitrary two-dimensional materials into each other, and even we can change the angle between them. And this is somehow giving us a unique node between superconducting orders in the van der Waals world. So what is important to keep in mind is that in the very same way as all compounds, we can control two-dimensional superconductors using pressure, chemical doping, and all the conventional knobs. But apart from that, we can use both, let's say, gating in two-dimensional materials, or twist engineering, or just creating heterostructures to try to drive a certain superconducting state towards a superconducting state that is a little bit more unconventional. And that is essentially the idea that we are going to exploit today. So if you think now about what is perhaps one of the paradigmatic examples in which spinability comes into play, maybe one of the most popular ones is the case of twisted bilayer graphene, in which just depending on what are the angles or the biases that you put in two layers of graphene, two layers purely of carbon atoms, you can go from superconductors to covalent insulators, to quasi-crystals, to strange metals, or to topological networks. So in the very same way that we are capable of creating radically different electronic states just with graphene, we may dream that perhaps by playing this very same trick, we may be able to create radically different types of superconducting states in two-dimensional superconductors. So that is the story for today. So today I'm going to focus on two very specific examples of this strategy. The first one, how we are going to create a topological superconductor by combining a 2D superconductor and a ferromagnet. And then the second one, how we are going to create a nodal superconductor just by exploiting a 2D superconductor that is very, very close to a quantum phase position. And before going to the physics, let me emphasize again that all the results I'm showing today are the work of many people that are not here. In particular, I'd like to thank all the people in the atomic scale physics group, Somesh, Mohammed, Marcus, Ling Hao, William, Shabudev, Mohammed, and Peter for all the wonderful experimental work that I am presenting today. And of course, I would also like to thank all the two PhD students in my group, Wanse and Mariam, that essentially work on the theory of what I'm telling you today. So let's move on with the first idea, how we are going to create a topological superconductor using a 2D superconductor and a 2D ferromagnet. So the idea for this is actually quite simple. So if you think about topological superconductors, these superconductors are just superconducting states that have a very simple property, which is that they are topologically non-trivial. And this essentially means that if you look at the bulk of the superconductor, you see a full cap. But now if you look at the edge, you see capless states that are topologically protected, and they are actually of Majorana form. Of course, topological superconductors are, let's say, very exciting for many reasons, including fundamental and applications, but they have the drawback that they are extremely hard to find in nature. And to try to overcome this limitation, there have been many strategies that try to engineer artificial topological superconductors by combining there will be different electron orders. And in particular, they have been proposals between, let's say, nanowires, two-dimensional semiconductors, van der Waals materials, and even topological states to create artificial topological superconductivity by combining the partial orders. So today I'm going to focus just on one of this, which is the case of van der Waals materials. And so from the theory point of view, if you wanted to do your own topological superconductor, actually the recipe is very, very simple. So the only thing that you need is first to have helical states in any form that you can imagine. So you can get them from the topological insulator, you may engineer them by yourself by combining exchange fields, right finger cutting, or any other symmetric strategy. And then the second ingredient is that you just need a switch for conductivity. And then if you play this game, you can essentially generate all the different strategies for creating an artificial topological superconductivity. So this is maybe one of the important points for what I'm going to tell you later on. So now let us focus on this case of topological superconductor with van der Waals. So a couple of years ago, there was an experiment demonstrating the emergence of topological superconductivity in a heterostructure combining 2D ferromagnets with a 2D superconductor. And the idea is that in this system, one engineers a helical electron gas by combining pressure finger coupling and exchange field, and then once the superconducting nitrogen enters, that drives the system to a topological superconducting state, giving rise to topological edge modes at the edge. So now maybe the question at this point is the following. So these are two-dimensional materials, right? And as two-dimensional materials, they are misaligned. There's a Moire pattern between them. So a valid question is there any role in the Moire pattern, or is the Moire pattern just a perturbation that we shouldn't care about? And to answer this question, let us focus first on a much, much simpler case, which is the case of a one-dimensional system. And this is just for to, let's say, factor out just this notion of having two-dimensional system. So if you think about a one-dimensional system and you ask yourself the question, well, what are the conditions for me to create a topological superconductor in a system? Then the answer to that is that, well, you may want to create your helical gas by combining pressure and exchange coupling. And when you do that, you essentially have a very small range of chemical potentials in which if you put your chemical potential there, when adding superconductivity, the system becomes a topological superconductor. Meaning that if you have your one-dimensional system and you just put your chemical potential at 0, that is not going to become a topological superconductor. Only when you put it on the green regions, that becomes a topological superconductor. Now, the idea is that if you have now this one-dimensional system, but with a Moire potential in one dimension, then your band structure is a little bit more complicated, right? Instead of having one band, you are going to have many bands simultaneously that come from the folding of your electronic structure in the millimeter zone. And now the idea is that once you do that, essentially, you are going to open many other regions in the phase diagram that are capable of showing topological superconductivity. So that is much easier to see if you just look at how the electronic structure is with the Moire potential, and now you analyze every single energy interval in which you can have topological superconductivity. And now you see that there's a whole range of intervals, even close to charge neutrality, in which you can now have a topological superconductor. So in other words, if you just compare the range in which you can have topological superconductivity without the Moire and with the Moire pattern, what you actually observe is that the Moire pattern allows you to create topological superconductivity in a much bigger range of chemical potentials. And that is essentially telling you that actually a Moire pattern in an artificial topological van der Waals superconductor may be extremely helpful for you to get topological superconductivity. And without going into the details, let me just say that by doing relatively precise estimates using both density function theory and time-bounding models, we believe that a Moire pattern is absolutely mandatory in this system to get topological superconductivity. But let us focus a little bit more on, let's say, what are the consequences in real estate, right? So what we do know is that we do have a topological superconductor. So let us first look at our sample, right? So in our sample, we essentially have a Moire pattern because our system is twisted, right? And as we have a Moire pattern, we can start asking ourselves, is there some consequence of this Moire pattern in real estate that we can actually demonstrate, both comparing a model with a data? So the answer to that is actually fairly simple. So if you now consider with the full model of your system, including the Murray pattern, essentially what you have is the typical Hamiltonian for the system that contains both kinetic energy, Riffelson coupling, superconductivity, exchange field, and so forth. But what is most important is that every single parameter in this Hamiltonian is modulated. And I am aware that this is kind of a monster Hamiltonian, so let me just emphasize one of the most important terms from the quantum chemistry point of view, which is the exchange coupling, which we do know that the exchange coupling is going to change dramatically due to this coupling, just because super exchange couplings depend extremely strongly on the local geometry. So essentially, the exchange coupling of your Mars superconductor is going to look like the picture that you have on your left. And now, if you look at how we see the IDE of your system, of the experimental system, you actually see that your bulk state, your bulk U-shift state, somehow follow a modulation that is suspiciously similar to the Murray pattern. And of course, you can do the simulation of the full model with this exchange profile and see how your bulk U-shift states look like. And what you essentially see is that indeed the U-shift states are going to follow the exchange profile. And of course, which is the same that you saw experimentally. All right, and of course, associated with this, let's say, exchange profile, we are going to have an electronic structure that is not the original electronic structure, but the Murray electronic structure. So now let us look at, not at the bulk anymore, but let's look at what happens at the edge into the Murray pattern. So we are going to take an island like this one and see how the bulk U-shift states are and how the edge states are. So if you first look at energies that are, let's say, not in the gap, what you actually see is that there's a maxima following the Murray pattern, as you can see on the picture on the left. And if you do the calculation, you of course see the very same pattern, which is essentially the same result that you saw before. Now, if you look at what happens at zero energy, at energies in which you have your induct topological states of modular nature, what you actually see is that the very same periodicity of the Murray pattern appears in the edge states, which is of course something that naturally appears on the theoretical model. So to sum up, essentially what we do know is that in this topological superconductor, the Murray pattern is critical. It has extremely important impacts on the both U-shift states and the edge states, and perhaps if it is removed, the topological superconducting state may disappear. So now let us move on to the second part, which is how we can create a nodal superconducting state from a monolayer that is close to a quantum field. And now the idea is that instead of thinking about a complex heterostructure, we are just going to consider a single monolayer, in particular a monolayer of tantalum disulfide. So the story for this part is actually very simple. So there are, of course, a huge variety of superconducting states, in particular conventional superconducting states, but let me just highlight two of them. So the simplest superconducting state is a S-wave superconductor that is fully gapped, and it usually comes from the conventional electron-phonon interaction. And then if you look at all the possible superconducting states that can appear, there are, of course, also nodal superconductors. And in particular, let me just emphasize here that we are going to think about an F-wave nodal superconductor because it's compatible with the electronic structure of tantalum disulfide. So the idea is that, let's say, for quite some years, we have considered selenide, tantalum disulfide as conventional superconductors, as the superconductors S-waves symmetry. That is maybe not the whole story, and there have been hints for many, many years that many of these materials are actually strongly correlated, or at the very least, very close to a quantum distance. In particular, there's already a work from some people in the audience here from 8 years ago showing that tantalum disulfide may actually be an F-wave superconductor, and even in a related component called iodine diselenide, there have been hints of the existence of legged modes stemming from the proximity to a F-wave superconducting state. So we are going to follow on this road and see if we can actually, let's say, map better how the superconducting state of tantalum disulfide is. So the message of this part is that essentially in tantalum disulfide there can be two superconducting states, and depending on how your sample is, you are going to get one or the other. And in particular, if your sample is very dirty, you are essentially going to get an S-wave superconducting state. But if your sample is ultra clean, you are essentially going to get an F-wave superconducting state. That is, of course, not all. And now let's dig a little bit more into this here. So the basic idea is that for an S-wave superconductor, as you know, if you have non-magnetic disorder in the wake coupled limit, the superconducting state doesn't change, or at least it is extremely resilient to weak disorder. This is what is called Anderson's theorem, and one can essentially see it on the picture on the left. Now, if you think of an F-wave superconductor, since the gap is changing sign, the Bernoulli zone, once you add disorder, you're essentially going to quench the superconducting gap. So you can think that once you add disorder to an F-wave superconductor, that is going to be detrimental to a potential F-wave superconducting state, but not detrimental for a potential S-wave superconducting state. And therefore, that's how you should rationalize the previous picture that I showed you before. So essentially, if you look at the electronic structure, the reason why you have a nodal gap is because in the why you have a nodal gap in the F-wave is just because if you think first about the S-wave superconducting state, your whole electronic structure has a gap because your gap is uniform in reciprocal space, whereas for the F-wave superconducting state, some parts of your electronic structure get a gap and others don't, just because of the symmetry of the F-wave superconducting state. And of course, once you go to once you map the whole Fermi surface in the F-wave superconducting state, you see that some parts of your Fermi surface remain gapless even in the superconducting state, just because of the existence of nodes in the superconducting gap. And that is essentially the reason why you have this V-shaped density of states. So now let's look at the data. So we are going to pick first a sample that is 30s, which is the picture that you essentially see on the left. And then if you essentially measure the sample and look at the DIDB, you essentially see that it can be, let's say, let's say fitted by a conventional S-wave superconducting gap. But now if you go to a much cleaner sample, the first thing that you see is that your gap becomes suddenly much smaller, and then that the gap actually becomes better by using a Dines fit, by using an F-wave fit. And now you can ask yourself, well, actually, maybe that gap is not an F-wave gap, but it's actually a Dines gap. And of course, we check that. And the bottom line is that if that was a Dines gap, you should have a negative correlation between your superconducting gap and the Berg breaking effect. And what we observe is a positive one. What this essentially means is that that gap that we believe is an F-wave gap, it's at the very least not consistent with being a Dines gap. But that's not the whole story. So something that is actually very, very interesting is that if you look a little bit above your superconducting gap, you suddenly see the existence of many body excitations that we call hidden order fluctuations, just because we don't know its exact nature. And what is perhaps especially important is that this kind of fluctuations appear in strongly correlated superconductors and are usually associated to spin wave fluctuations. And then even if you start looking at what happens with applied magnetic field, what you essentially see is that after killing the superconducting gap, a pseudo gap starts opening once you apply large magnetic fields. So this is essentially everything that I wanted to tell you today. So if I can ask you to remember something from today, I would ask you, please remember that van der Waals materials, and in particular, like Cogenite materials, are a potentially very interesting platform to engineer both topological and nodal superconductivity. So thank you very much for your attention.
Thank you. So the talk is open for comments, questions. Yes.
Thank you, very nice talk. So you say F-wave because of the nodal nature of the gap, right? So it cannot be P-wave or D-wave. I'm just curious about what makes you think it's F-wave and not any other way.
So we don't see nematicity, right? If it was P-wave and nodal, it would have to be also nematic. So essentially, F-wave is the simplest superconducting gap structure that is compatible with having a nodal gap and not having nematicity, which is essentially what we see experimentally. It doesn't mean that there may be more complicated gap structures that are also consistent.
Also, with F-wave, you are bound to have spin flip. You don't have symmetry. So S-wave and F-wave are very constrained in that sense. So that's what you may mention. So there must be a different mechanism causing this F-wave altogether. There's no phone on the
Yes, exactly. So that mechanism is, of course, something that we cannot say at this stage, but it might be related with the many-body hidden order fluctuations we observe. And of course, it is not possible to say at this stage.
Thanks. Yeah, this question. What about the excitation? The excitation of you did not see below the distribution. This is actually similar to what I saw also. But so what do you think of it? Is it like blue or what did you increase the temperature? For example, you see that this excitation is this.
So you're referring to this one, right? So so if you apply a magnetic field, this fluctuation survives. So which tells you that it's not really dielectric mode. If you increase the temperature, of course, at some point you don't see anything, probably because of thermal. So it is not easy to say if it disappears with temperature or doesn't. What is clear is that it is not, let's say, a consequence of the superconducting state, but it survives, let's say, applying magnetic field. And perhaps what is a little bit even more interesting is that it is much stronger in the hidden samples rather than in the direct ones. So it is much stronger in the samples that we believe are F-wave superconductors.
So it is broadly called a mechanism.
It might. Of course, it is impossible to say at this stage, right? But
Thanks, excellent talk. In the first part, in the heterostructure, do you need a magnetic honeycomb lattice to get the current Majorana modes, or it could be different geometries?
yeah, that's a very good point. So in principle, any magnetic lattice would work. So the underlying structure of the magnetic lattice is not important. What is important is that you create an exchange field with the superconductor in the out-of-plane direction.
Can you repeat the argument? Why did you say experimentally that for the strong disorder limit, that it is S-wave? Because if I look at the LDOS or the DOS basically, it looked like nodal, right?
So yeah, I mean, it looked like nodal, but if one doesn't fit, the fit is much better with S-wave with thermal snare. So for example, if you just fit your EIDB with let's say S-wave at the temperature of the sample, you get an almost perfect fit. So essentially, there's no reason to consider something else. If you try to fit with F-wave, you get a much worse fit. I mean, of course,
that can happen due to disorder because you are fitting average density of state, and with strong disorder, you can have bubbles of different. So the fit can be worse because of disorder. But what rules out the fact that F-wave survives still strong disorder? Because you have not quantified the strength of the disorder, so it might not be strong enough to kill F-wave. Because in case of strongly correlated D-wave, it can be protected against disorder. So it might be the case because this is extremely strongly correlated system that the F-wave survives strong disorder.
All right, so you are saying that the material is essentially F-wave all the time?
Yes, yes. What rules this possibility out? That's what we mean.
So let's say from the data that we have, I would be confident in saying that with strong disorder, the system is S-wave, and of course there are reports of other samples where they see a clear S-wave gap. So at least for tantalum disulfide, there's some situation in which the system, it is an S-wave superconductor. And we tend to believe that the strong disorder limit is the limit in which at least this material would be a S-wave superconductor. Now, maybe the question is if there's some other limit in which it may be not a S-wave superconductor.
Thanks.
Okay. So I think we have to move on. Let's thank Jose again. So the next presentation will be given by Sebastian Perez from the University of Zaragoza. And the title of the talk is Interfacing Magnetic and Superconducting Quantum Circuits.
Así, ¿sabes? Le puedo quitar las carillas, ¿verdad? Thank you. Thank you, Peter. Sorry. Okay, thank you very much for the introduction, Peter. So, as you said, my name is Eva Martinez, and I come from the Institute of Material Science in Zaragoza. And I would like to start by thanking the organizers, especially Isabel, for inviting me. It's a real pleasure to come back to normal conferences again. Today I will. Okay, thank you for that. Sorry. Okay, I will show you some experimental and theoretical work that we are performing in the framework of an EUC grant that has just started in September last year. That is directed towards the study of quantum harmonic systems, okay, using superconducting circuits. Okay, let me start by very briefly introducing what magnets are. As you know, magnet is simply the quantum version of a string wave. If you think of the simplest string wave, that is that with infinite wavelength, or that is the same with k equal to 0, you can think of this excitation spectra as a harmonic oscillator in which all levels are equally spaced, and each energy level corresponds to fitting one single string. Of course, in reality, this doesn't not take place this way, but this modulation is shared among all the strings in the ferromagnet that precede all at unison. Okay, the so-called hidden mode. What happens if you put this system in strong coupling with a quantized field of bosons, for instance, photons in a cavity? Well, if the coupling between your magnetic resonator and your photonic resonator is strong enough, you will have the a modulation in time between states that corresponds to having one magnet in your ferromagnet and 0 photons in the cavity, and states in which you have 0 photons in the ferromagnet and 1 photon in the cavity. This goes on, okay, at a frequency that is called the Rabi frequency, that is nothing but the coupling, the strength of the coupling of your two systems. Okay? If you achieve this regime, you say you are in a strong coupling regime in which the coupling is larger than the losses in your systems. Okay? One experimental signature of this regime is the opening of an avoided crossing at the point where both resonators should be degenerated. Okay? Achieving this regime is extremely important, as we will see in quantum technologies, for the following reasons. Okay, for the reason we will see later. Sorry. The first time this phenomenon was observed in magnetic crystals was in the group of Ross in Munich in 2013, where they observed the opening of this very nice avoided crossing. Okay, when putting a relatively bulky piece of Gibbs crystal in a superconducting coplanar wave resonator. Okay, why are these magnetic systems interesting for quantum technologies? Well, there are many reasons. Maybe the most well known of them is that magnets interact with both photons in the microwave and the optic landscapes. Okay, this tells us or suggests us that one could think of building transducers between microwaves and optical photons. Another interesting feature is that theoretically actions, okay, the particles should be able of exciting magnets. So if one is able of design an experiment in which single magnets can be detected, okay, one could in principle construct a very nice action detector for dark matter searches. Another interesting proposal is the use of magnets as cavities, okay, as they are a bosonic field of excitation, just like photons. The nice thing of magnets is that their wavelength is extremely short if you compare with the with the wavelengths of photons, okay, in resonators at the same frequency. And finally, one other nice thing about ferromagnetic materials is that they exhibit reciprocity. Okay, reciprocity means that if you send a signal in two directions, you should obtain the same result. But non-reciprocal materials allow you to think of devices like shifters, isolators, or circulators that are extremely important in quantum technology. Okay, all these applications and most work that has been done up to now is focuses on the use of homogeneous modes, like the Kittel model that we have just reviewed, and almost always G. G is a ferromagnet that exhibits the record low damping times. Damping parameters, so record long damping times. Okay, so first of all, let me show you some preliminary experimental results that we have obtained when performing strong coupling between magnons, okay, and photons in transmission lags that allow us to perform broadband ferromagnetic resonance. This is a coplanar wave-type music time in which we open a very thin constriction. This opening allows us to strongly focus the zero field point fluctuations in the resonator, as you can see in this simulation, where you can see the 0 point RMS magnetic field fluctuations at 1 GHz achieve values of the order of several hundred nanometers. Okay, so we have located different samples of ferromagnetic materials with different shapes close to this constriction, and we have performed conventional transmission experiments. In these experiments, we focused on permalloy. This is a material that, of course, does not exhibit such impressive damping rates as Z, but exhibits a much larger saturation magnetization, and is also nice from a fabrication point of view because it's very simple to fabricate and to integrate into circuits. These are the experimental results we obtained. You see these really nice curves that show you the dependence on the resonant frequency of your ferromagnetic resonator on the magnetic field. Fitting this to the Kittel formula, it's very easy to obtain the magnetizing factors of the samples that are very nicely with the shape, different shape that we have been studying, ranging from almost square shape down to an extremely thin nanowire having just 600 nanometers in diameter. Okay. Next thing we did was to turn these transmission lines into resonators, just by simply opening gap capacitors at given positions. Okay. In this way, we could choose the cut frequency, an interesting cut frequency for each material, and cut the resonator at this specific frequency. Okay, if the coupling between the ferromagnetic resonator and the photon resonator is strong enough, as I said, one should expect the opening of avoided crossings in the transmission spectrum. That is exactly what you see here. This line corresponds to the very slight dependence of the resonant frequency of your niobium resonator with the magnetic field, and here at the point where the magnetic response cross, there is the opening of this very nice avoided process. From this, we extract experimental coupling factors that let me also highlight that agree very nicely with the theoretical values that we estimate from numerical simulations. So numerical simulations kind of work. Okay. Let me also highlight that in this case we'll take couplings that are close to 200 Hz per spin. This is a very large value. To see that when we compare it with coupling factors that we also obtain experimentally when depositing free radicals that are spin equal to 1/2 molecules over superconducting resonators using deep penalty method. Yeah, we also observed the opening of this avoided crossing, and we extracted also a G value of similar order. Okay? Let me highlight that here we are dealing with individual spins that are deposited
with extreme precision over the transmission line, the central conductor of the resonator. Well, up to here we have only been seeing things related with homogeneous magnetic modes, but as you know, ferromagnetic materials offer us a much richer and nicer amount of magnetic excitations that some of them exhibit even topological properties. One can think of, for instance, magnetic defects. Magnetic defects are protected and can be moved through samples, okay? Giving us much flexibility and some interesting properties for applications. In the easiest case, imagine you have a missing spin system in which spins can be point up or down. In three dimensions, the easiest magnetic defect you can think of is a planar domain world separating two domains with opposite magnetization. If you let your spins move on the plane, you can think of the vortex line as an effect, okay? That joins the central part of these couplings of the magnetization, and if you let your spins rotate in three dimensions, you can think of the plot point or magnetic monopole. Okay? If you translate these topological defects into the real life, you will get these very famous, very well-known structures that are the domain wall, the magnetic vortex that you can synthesize, stabilize very easily in ferromagnetic disks, or the Selenium. I will focus on the study of magnetic vortices. Okay? Vortices are interesting because, on the one hand, they can be stabilized in disks, having sizes between few microns down to few hundred nanometers, offering us a very large modulation of the magnetization, okay? Very large gradients. This is also reflected in the strong spatial focusing of the magnetic field that this structure creates, okay? Where the magnetic field are concentrated in very small regions or few 10 nanometers. Nice thing about vortices is that their frequency can be tuned, and also they can be moved, and this can be achieved by means of externally applied fields, or even more interesting, by means of spin currents. Finally, vortices exhibit a very rich excitational spectrum in the range of few hundred megahertz up to few gigahertz. Okay? So in the range of frequencies that we are normally interested in quantum technologies. The first mode is the gyrotropic mode, in which the vortex receives around the equilibrium position, and you can also find azimuthal modes, radial modes, etc. These modes are very nice because they can be used to excite, for instance, the inversion of the magnetic vortex core, or for instance, as you see in the simulation, to generate spin waves, coherent spin waves. Well, our purpose is to study, to address the dynamic properties of these objects by two means, using superconducting sensors like YBC or nanosquids, and coplanar transmission lines and Telomere resonators. In the first case, regarding squids, this is done thanks to the collaboration there and the University of Tübingen. We are working in the development of broadband, let's say broadband nanosquid sensors that would allow us to extract the most bandwidth and to be able of sensing the properties of these objects with short time resolution. For this purpose, the plan is to short a transmission line with a nanosquid. Here you can see some preliminary devices of YBCO and LGO light crystals. Okay. Nanosquid sensors also allow us, of course, to perform some basic characterization. Okay, one of the first things we did was to investigate the limits or the possibility to stabilize vortices in the smallest disk possible, or in the smallest particles that you can imagine. For this purpose, we fabricate very small disks having just 100, 200 nanometers in diameter. Okay? We verify by electronholography that vortices are indeed nucleated in these particles, and we perform magnetization measurements with the nanosquid. One very critical question here is if the vortex state is indeed the ground state of this piece. Okay? Thanks to the fact that we could perform nanoscale measurements at variable temperature, we could characterize the energies involved in the processes of vortex creation and vortex annihilation. Okay? And from this, you can extract information about the energy values that are involved in the process, and we could conclude that the vortex state is indeed the ground state of these very, very small magnetic disks. Different thing we could do was to try to control some parameters of the vortices. Okay? For instance, the circulation. That means if spins are curving clockwise or counterclockwise. This can be controlled by breaking the symmetry of the disk and then by changing the field at which the vortex is nucleated. Okay, this was experimentally verified thanks to the using nanoscale magnetometry by performing complete or incomplete hysteresis loops. In each of these loops, the vortex is nucleated either at positive or negative fields, that means nucleated a different sense of circulation, and from the differences in the annihilation field, we can be quite confident that we are controlling indeed the circulation of these objects. Okay, and now, just to finish my presentation, let me briefly tell you about our progress in the study of these dynamics using superconducting resonators and transmission lines. This is done thanks to the collaboration of Alicia Gomez in India and Canada. Okay, here you can see we have started already to try to study different magnetic materials having nice properties in terms of damping factor. Okay, we don't want to use jig because although jig exhibits the best damping factor, it exhibits extremely low saturation magnetization because it's it's a ferromagnet. Okay, this is not a very good idea if you want to stabilize vortices because you need as large as possible saturation magnetization. For this reason, we are now investigating alloys of cobalt and iron that should yield values of very nice values of the damping factor and very large values of the saturation magnetization. Here you can see some of the disks we have been fabricated that are located in very good contact with constrictions in transmission lines. This experimental work is still in progress. From our theoretical estimations, however, we can already expect that achieving the strong coupling regime between these ferromagnetic resonators and photons in cavities is indeed possible. This is a simulation of the let's say strong coupling condition, meaning that above 1 it means we can achieve strong coupling and below 1 we cannot. Okay, that is calculated for these having different diameters and for different values of the width of the constriction performed in the resonator. As you can see, for these as small as 200 nanometers in diameter, achieving strong coupling should be indeed possible. Okay, what is even nicer, we verified that this strong coupling regime can be achieved also for the high energy modes present in the vortex. This is nice because as I remember you that these modes can be used for other applications like very fast switching, the magnetic vortex code, or the generation of spinels. Finally, we are now studying theoretically the possibility and the advantages of using these structures as magnetic cavities. Okay, so far only homogeneous spheres have been proposed as cavities. For this implementation to be successful, one needs to bias the thing at relatively large fields. I remember you that normally you want to read out these states using resonators that are superconducting. So normally you don't want to achieve such large fields, and that the spatial region in which you can achieve nice couplings is around the whole sphere. The magnetic volume of this resonator, which is the parameter that tells you how strong your coupling will be is extended around the whole sphere. If you use vortices, the nice thing is that your magnetic fluctuations, your zero field background fluctuations, are focused in very small regions of few nanometers. Okay, so you could even be able of choosing, of selecting very small populations of fields. Okay, this vortex can be also moved around the surface, so you could think of this device as a kind of scanning probe. Okay. A second really nice thing of this is that, as I told you, this resonate even under no externally applied magnetic field. Okay. Finally, our numbers tell us that these cavities should yield coupling factors that are extremely large, of the order of megahertz. Then we remind you that using superconducting resonators, conventional superconducting resonators, you normally are able of creating few hundred nano Tesla, okay, and 0-point fluctuation field that translate in few kilohertz of coupling. Okay, so just to finish, let me summarize by saying that all these studies and these strategies at investigating the combination of these vortex cavities with superconducting cavities to perform useful tasks for quantum technologies. For instance, one could think of combining different vortex states that could eventually help in assessing or communicating individual speed units. You can think of this also as a very sensitive sensor that has spatial resolution of few nanometers in diameter, etc. And with this, I have come to the final slide of my presentation. I would like to thank all the people in my group that have contributed to this work, especially people from the University of Tübingen and India. Okay, thank you very much.
So the talk is open for questions, comments. Maybe I can start with a more technical question. I mean, you put this, I think this prototype is somewhere close to the constriction, but not on top of the constriction. Later on, we show the copper iron on top. Does it matter?
Sorry, so again?
I think, yeah, here you have this copper and iron directly placed on top of the constriction here. And I think the Faraday was before the way. Does it matter or way?
You mean this, for instance?
No, it was much earlier. I think it was Faraday.
Well, I think I didn't show any picture of the permalloy disk on the nanosquid. Actually, yeah, actually here the first idea is to locate the permalloy exactly on the constriction. Yeah, this is extremely important. This might be well seen maybe here. I mean, these values of the G factor are only achieved if the size of the constriction matches the size of the disk, or even below. This is extremely important.
So W is the width of the constriction.
Yeah. Yeah, for instance, these numbers here, of course, pattern in the nanoconstriction increases in the end, the strength of the RMS magnetic field fluctuation that the RMS current takes. And this also happens in a very small region around the constriction. Actually, this is what determines the volume of this mode, no? Because the coupling in the end depends on the frequency. Essentially, it's the frequency divided by the volume of the mode square root. So the larger the frequency, the larger your random fluctuations are, and the smaller the volume, the better.
I was referring to that image. So here the permalloy is.
Okay, sorry. Yeah. No, because I put this image because I'm not on the process. No, this is an OmniPro tip that we use to locate the sample on top of the constriction.
Okay.
Yeah, now that the nanowire is located precisely on top of the constriction. Here you can actually the resolution we achieve is impressive because this constriction is only 200 nanometers in diameter, and this is the nanowire that is really.
Last chance for further questions. Okay, so let's thank Pepper again. Okay, then we come to the third and last talk of the session, which will be given by Alicia Gomez from Umbea Nanoscience. And the title of the talk is Superconducting Resonators for Space and Quantum Applications.
Hola. Okay, so thank you very much. So my name is Alicia Gomez and I come from Telomere Biology. As he just said, I'm going to talk about superconducting resonators for space and quantum application. It's going to be a little more applied than the previous talks, but I hope that you will be in the last one. And thank you for the organizers. Sí, entonces no. So all the work that I am going to present today was not done by myself, of course, but we are a big collaboration between biology and nanoscience. The part of space is done in collaboration with Universidad de Cantabria, and the part of quantum computing in the group of Fernando Luis in Zaragoza. Also, most of the work that I am going to present is part of Marina Carrero thesis, that is somewhere there. So, what are superconducting element resonators? What are the resonators that we are developing? At the end, what we are going to have is a transmission line where we are going to have parallel to this transmission line an LC circuit, an inductor and a capacitor that is going to be absorbing the energy that is going through the transmission line at a certain resonant frequency. Here you can see the picture of a real pixel where we are going to have the transmission line, the inductor, and the capacitor. As I told you before, what is going to happen is that out of resonance, all the power is going to be transmitted in the transmission line. You could see it here. But when we are in resonant condition, the energy is absorbed by the resonator, and it is going, for instance, to induce a current in the inductor. There are several parameters that can be tuned depending on the application. The first one is going to be the resonant frequency, that depends on the inductor and the capacitor. The second one is going to be the quality factor, that is going to give us information about the losses in our resonators. There are several contributions. One of them is the internal quality factor, that depends on the superconducting material. And the other one, for instance, is the coupling quality factor, that depends on the coupling between the resonator and the line, or even the coupling between the resonator and the ground plates around it. Finally, the impedance is going to depend also on the inductance and the capacitance and can be tuned as wish. All of it by microwave electromagnetic simulations. The good thing about this type of lamp element resonators is that I can have a single transmission line and couple parallel to it a lot of resonators. Here you can see a real example where I'm going to have this orange transmission line and 80 pixels coupled to this single transmission line, which, for instance, in space is very important. Which are the good things about these resonators? They are going to have a very high quality factor, so low total lifetimes and low losses, which at the end also means low noise or high sensitivity as detectors. They are frequency multiplexable, so I can do large format array camera, and I can tune all the parameters that I just told you. In particular, we are working on developing this type of superconducting resonators for two main applications. The first one is as kinetic inductance detectors, and the second one is for quantum applications. I will start with the first one.
kinetic inductance detectors. So just a little bit of introduction about the space. Here I show you an example of the last mission that has been launched by ESA to study the cosmic microwave background radiation. If you can see in the evolution of time, you can see that we have higher sensitivity, but also higher resolution in space. For the future mission, which was submitted to ESA, what was required was higher number of pixels, polarization sensitivity, and also lower noise. Here, you can see the noise of the detectors along the years, and the blue ones represent the semiconductor detectors, whereas the yellow ones, that are the last one that has been developed, has order of magnitude less noise than the semiconductor traditional detectors. On the other hand, you can also plot the number of detectors in an instrument as a matter of the years, and you can see also how the superconducting detectors has reached the maximum number of pixels in a single instrument. Therefore, superconducting detectors are a very good technology for future experiments. Among the superconducting detectors, there are several types. One of them are the transition edge sensors, which has very, very good sensitivity. However, as you can see here, they are very difficult to fabricate, and also it's very difficult to include a large number of pixels. The other alternative are the kinetic inductance detectors, which has lower sensitivity, but is very good also. And also, as I told you, you can include a large number of pixels very easily, and they are easy to fabricate. This is where I'm going to focus. How do they work? Imagine that we have our superconducting material, and this is going to be a pair breaking detector. What does it mean? That a photon, if it has energy enough higher than the superconducting gap, is going to break our Cooper pairs and is going to create quasi-particles. These quasi-particles are going to change, in this case, a property that is called the kinetic inductance, and therefore, by following the change in the kinetic inductance, we are going to have information of how many photons has reached our detector. How can we measure it? If we go back to our Rampere microscope that I explained you at the beginning, as we are now dealing with a superconducting material, the inductance is not only going to have this geometrical part, but is also going to have the kinetic inductance. Therefore, when a photon hits our detector, if it is absorbed, the kinetic inductance is going to increase, and therefore the resonance frequency is going to decrease. By following this change in the kinetic inductance, we get information about the photon that has been absorbed by my detector. You have to tune several things to make it work. For instance, one of them is going to be the superconducting current. Imagine that we are in the CMB and we want to be sensitive to the W band. In this case, aluminum, the frequency cutoff is going to be 100 GHz because the critical temperature is 1.2, more or less. What means that below 100 GHz, the photon is going to be reflected. For instance, in this case, what we have done is using proximity effect with titanium aluminum bilayers, we have decreased the critical temperature to 80 millikelvin, and here, as you can see, the frequency cutoff has diminished from 100 GHz to 50 GHz by using this proximity effect bilayers. But also, you have to do some geometry design, because in our case, the inductor is going to be the absorber or the antenna. For instance, you have to tune the effective impedance so that the free space impedance matches the impedance of the detector. The inductor has to be like a solid absorber for the radiation, like the one you can see here. And also you have to change the geometry of your inductor depending on the polarization that you want to sense. Following these steps, we have developed a titanium aluminum lattice for the CMB observation in the W band. Here I show you only a single pixel that is going to be sensitive to the vertical polarization, and the area of a single pixel has to be in the order of the wavelength that you want to detect. In this case, it's 3 millimeters. Here in the graph, you can see the whole camera that includes 1000 pixels, but imagine that we only focus on one of them. Here we can see the resonance frequency, and we start sending photons to our detector. What we are going to see is the kinetic inductance is going to increase, and the resonance frequency is going to decrease. Therefore, we can see like this that our detector is sensitive to this radiation. Actually, By changing the wavelength of the photons that we are sensing, we can determine the frequency band of our detector, which is 100 in 80 gigahertz, which is suitable for application of the CMB studies. But as I told you at the beginning, we need to be sensitive to the dual polarization. So we have developed this dual polarization structure, this big structure, where one of them is going to be sensitive to the vertical polarization and the other one to the horizontal polarization. You can see here that the band is detected again in the W band, and we can distinguish between the two polarizations. However, for going to space, we don't only need to use it in the lab, but we have to increase what are called the TRL, that is the technological readiness level, for going to space. For this purpose, we are working in several ground space telescopes, putting our detectors, for instance, in the KISS instrument, which is installed in the Instituto de Astrofísica de Canarias, in the Canary Island, or the NICA-2 instrument in Granada, in Sierra Nevada. Okay, let's go and move to the second part of the talk. The other application of our superconducting detectors is its application for quantum things, as Pepa just told you before. In particular, what we are working in collaboration with Carlos Zaragoza is that they propose not using, well, people propose and they are expert on it, not using only bits, the traditional superconducting qubits, but what they say is, okay, let's use molecular spin qubits as our basic unit. It has several advantages, at least high reproducibility, tunable, they can do chemical engineering to tune all the properties that they need, and it is scalability. However, we need a platform to interact with these molecular spin qubits, and this is where the superconducting resonators come. Imagine that we are in the quantum electrodynamics regime, where we are going to have our quantum system that interacts with some photons that are going to be trapped in a microwave cavity. This, in the real world, will be this molecular system that you can see here, in this case in the shape of a crystal, and the superconducting lamp element resonator that is going to create the photons that is going to be interacting with the quantum system. There are several characteristics that are very important. For instance, the spin losses and the cavity losses that is going to depend to the quality factor that I told you at the beginning. At the end, what you need is to have a coupling that will be this G factor that is higher than the losses of both of the individual systems. This is critical and is needed to reach this strong coupling regime to be able to do non-demolition readout and use it as quantum computing. But how is this coupling mediated? The first thing that we need to do is to have our resonance frequency that is going to be tuned with the inductor and capacitors that matches the energy levels of the molecules that you want to interact with. Here I show you an example where we have a chip with 12 resonators, and as you can see here, the resonance frequency has been tuned to match the different energy, the different transition for this molecule. The lowest energy in the megahertz range are going to be tuned to the nuclear spin transition, whereas the higher energy resonators are going to match the electronic spin transition. Therefore, in a single chip, we can test all these transitions and having an on-chip laboratory. But again, how is this coupling mediated? What is going to happen, as I told you at the beginning, in resonance, a current is going to be induced in the inductor. This current is going to generate a microwave magnetic field that is, you can see here in the out of plane direction, that is going to mediate the interaction with our crystal. Again, by changing the inductor geometry, we are going to be able to modify this mode volume. For instance, if we want to interact with macroscopic molecular crystals, what we are going to do is to do a big inductor that is going to generate a big magnetic field volume. And here you can see the real example. We are going to have here the resonator, and we are going to place the crystal on top of the inductor. However, at the end, what we want to do is to reduce the number of pixels, the number of spins that we are going to be coupled to. Therefore, for doing this, we do what Pepa told you before, that is, we are going to reduce our inductor, so all the energy of the magnetic field is going to be localized in this part of the inductor, and we are going to be interacting with very few spins. Later, what we are going to do is to place the crystal on top of this constriction, and at the end, what we would like to do is to place a carbon nanotube in order to have a single spin coupled to the carbon nanotube. Sorry. Here I show you one of the last experiments, and that is part of Victor Royano's work. What they have done is to choose the traditional molecule that you can see here that has an electronic spin and nuclear spin. At the end, these values, what gives you is this rich energy diagram, where again, what we are going to have is some nuclear transition and some electronic transitions. Here you can see the reality, where Victor has placed here on top of it the crystal. If we focus in one of these resonators, what you can see here is the transmission of the resonator as a function of the magnetic field. What you can see is that some anti-crossings appear at certain fields that are the fingerprint that we are activating one of these nuclear spin transitions. This is critical, and it's the first time that a high cooperativity regime has been reached to molecular spin transition on a superconducting chip, and is the path for being able to implement qubits in this type of nuclear spin system. What do we need to do next? What we are going to do is now to include a readout line that is going to be able to read the state of our spin, but also a control line that is going to be able to operate the molecular qubit itself. At the end, these systems is going to allow us to use the nuclear spin for operation and the electronic spin for detection, having a single computer in a single molecule. However, as I told you at the beginning, the flexibility of our local element resonator has a broad application part. So, for instance, now Marina is working with Fernando in the capping to the electronic field that is created in resonance. At the beginning, I told you that it is going to create a current that is going to create a magnetic field, but it is also going to create a charge that is going to create an electric field and can induce also spin transitions. We have also started working with Eduardo Lee in capping our superconducting resonators to semiconducting nanowires for gaining qubits, and also with Pepa and Jesus Gonzalez from Material in capping our superconducting resonator to magnonic nanostructures. So, as summary, we have been working in the last year in developing superconducting element resonators for different applications, one in space as kinetic inductance detectors, with applications in astronomy, but also now in dark matter experiments. And we have developed some functional detectors in the W1. And we have also started working on developing lamp element resonators for spin quantum processors, where a high coupling to nuclear spin transition has been already achieved. So that's all. Thank you for your attention.
Yeah, thank you, Alicia. So the presentation is open for questions, comments.
Thank you, very nice talk. I have a very naive question regarding the sensors for the detector. Do you have any spatial resolution where the photon hits on your sensor?
Well, at the end, the photons in the region that we are sensing is 3 millimeters. So one thing that you have to do is that your pixel has to be in the size of your pixel. In any case, the optics I didn't tell here, but the optics in the cryostat, what it's going to do is to place the optical resolution in space in the telescope and focus in every single pixel. So you have arcosecond resolution depending on the optics and on the size of your detector. Yes.
But within the pixel, you don't have a spatial.
Within the pixel, no. No. No, because it is in the size of the wavelength actually. If you have it bigger.
Thank you.
There's another question.
So if you have to summarize, what would be the most ideal superconductor that would give the best response? Low gap high TC or low gap ATC?
For a for a space application?
Yes, yes.
Well, at the end, the best response not only depends on the critical temperature. This is an easy example because I didn't want to put here a lot of things. But the noise of the detector is going to be to depend on the quasi-particle lifetime. That this is the time you break a Cooper pair and the time that it takes to recombine to a Cooper pair. In aluminum, it is very high. And as this noise equivalent power is going to be inversely proportional to this, I have here the formula. I can go quickly. Yes, here. So this is going to be the intrinsic noise of your detector, and it's going to depend on this photon lifetime. That is why, for instance, it is usually we use aluminum because it has a very long photon lifetime. So it's not only the DC, the gap, there are a lot of things. It is also very important the sheet resistance or the resistance just before the critical temperature. So there are a lot of, depending on application, basically.
Yes.
Okay.
I think I may have missed it, but you mentioned for the space application that the detection of polarization is important. And how do you do that?
Well, in the Piketty structure that I told you at the beginning, at the end, what I have is a pixel placed like this and another resonator placed like this. And I read the response of this one and the response of this one. And then you can sense the degree of the polarization that is getting in your detector. This is for space. In here in ground, what you do is you put a half-wave tape that is going to rotate your polarization, and you have two different detectors. So, but in space, you have to diminish the space that your detector is going to take and mass and all these kind of things.
Further questions? Okay, that doesn't seem to be the case. So let's thank Alicia and all three speakers for their presence. I guess, you want to say something at the end before I pass on the word. Let me take the opportunity to thank Herman and the whole team for putting this very, very nice conference together in a record short time and showing that it's really possible in such a short time to organize such a nice workshop. I think we learned a lot and enjoyed being together here in this atmosphere. Thanks a lot.
Thank you very much. Yeah, thanks. So actually, I will say just a few words here, and we have our vice director for research, Daniel Jaque, who is going to, with your permission, to close the session. Okay. Maybe I can. Do you have the hard disk somewhere? Sí, no, lo pasamos, ¿no? ¿O qué quieres que...? Ah, no, lo que lo retransmites de aquí. Si pones el ordenador aquí, puedes transmitirlo ahí directamente. Vale, pero entonces tengo que estar en el Zoom, es que no sé, me he salido. Ah, no, entonces ponemos la chat de mi punta, ¿no? Sí. Vale, sí, yo creo que sí. Si no, ponme así. A ver, sorry. Vale. Gracias. Okay, so there is one important announcement, and it is about paperwork, right? So please, so our action will end in some weeks, and there are still things to do. In particular, there is one visit. There are two visits, but there is one which is particularly important, which is of an Ukrainian student who just now went out of Ukraine, and it's an investigation for him, and we need to make this paperwork very rapidly. And for this and for other reasons also, we really need that you make your own paperwork, each one of you, as fast as possible. So you all receive this email, just enter to the invitation link, and then follow the instructions as usual. And do not hesitate to contact Irene for any questions, okay? So, as you know, so please do this as fast as possible and just ask us any questions. Please do this maybe tomorrow or the day after latest, okay? So I think the action is not yet ended, but there will be one management committee meeting, but it will be an online management committee meeting, and we have to do that. And we will have our cost officer there, and so I think that at least the management committee will meet online once more, but this will be the last discussion. And well, we have our next action, and let's hope we get it. And as you see, we have been focusing on quantum materials, sensors and devices, and on the quantum systems. We have organized this around these three main ideas, and together to do things and to advance as we have been doing these years, but on a slightly different direction, and also with new members in the management committee. Some of them are here. So I think that at this point, I would like to give the word to Daniel and to thank him for having taken the time to visit us.
Thank you very much, Herman. So as Herman said, my name is Daniel, and I am now the Vice Rector of Research Policy at the university. So one of my main tasks is to thank the people who is working to improve the research in the university. And one of the directions is clearly to be able to coordinate European projects. So I have to thank in the name of Herman to all these people who work in the organizing committee, in the local organizing committee, the grant managing. But of course, I have to thank Herman because everybody knows what is the working load of coordinating a project. So it's the history, that every time that you try to motivate the people to cooperate in a coordinated project or a grant union, everybody wants to be in the consortium, but nobody wants to coordinate. So even in our university, we have few people that is taking the time and the efforts to coordinate. So Herman, I think everybody will thank you, but in the name of the university, I have to thank you special. Okay, so thank you everybody. Okay, yes, we can. So I don't know if you want to get the continuation of this course. I don't know. So I hope you will get it. It's good for everybody here. So this is a very good example of what European countries and European researchers should do, is cooperate and try to put all the energy together. Okay. So in this sense, I want to say in this special time, I want to say a few words. And this is the picture that we are using to show our support to the Ukrainian people and to all the people that not only for Ukraine, for other countries in Russia that's involved in this nightmare that all of us are living. So this is the picture, and there are two hands, one in blue, one in yellow, and I want to show you why, or I'm going to explain you why we choose this picture. 26 years ago, we have a very famous professor of law in the university who was teaching, but at the same time, he was working in the main jury of Spain, especially dedicated to try to stop or to put in jail all the terrorists, independentist terrorists from the north of Spain. At that time in Spain, we were experiencing very bad times with a lot of people dead per year. And this professor, Tomás y Valiente, by the way, Valiente means brave. Tomás y Valiente, Valiente was the surname. He was fighting strongly against the terrorists. When he was almost retired, he stopped his work in the jury, in the national jury, and he came back to the university to teach. And when he was teaching and was correcting exams for the students, one of the terrorists came to our campus and shot him and killed him. Okay? At that time was a very strong reaction in the whole country, but also in our university. It was our professor, and at that time, the sign that we choose is to put some white paint in our hands to show that this is my hand. I have clear hands. I don't want to be involved with this kind of history. And this is a very famous picture of our campus with a very big manifestation. So since 26 years, this picture is always with us in our campus. So it's an image of what we want to do with our hands. It's just be always clear. So that's why we choose this image to support this Ukrainian people and all the people involved in the world. So, okay, so this is, in my opinion, what is the one of this network that is for making research is a big example. It's a nice example of how we can develop and how we can solve problems in the future, working together in all the dimensions. So, thank you very much. As far as I know from my previous experience with cross-action, please do your homework, okay, your paperwork, and try to do that, because now is the most important, more than a paper, more than a nature of science. So thank you very much. Have a safe trip back to your countries, and enjoy the last hours in Madrid and Spain. Thank you very much.